Good morning, dear colleagues and participants. Welcome to the final day of the 10th International SAMSONOV Conference, Material Science of Refractory Compounds. Today we continue with the session dedicated of refractory metals and alloys, an important area of modern material science closely related to high temperature and advanced engineering applications. We sincerely thank all participants for their active contribution throughout the conference and wish you productive discussion during today's sessions. And now let me welcome our speaker, Alexander Ruch, to present the participants. Thank you.
Sorry, Branislav Gor now.
Okay. Excuse me. Yeah.
Yes?
Yes.
Hello, dear colleagues. My name is Alexander Rut, and I am chairman today's plenary session. Our session devoted to refractory metals and alloy, and the first presentation will be done by keynote speaker of our conference, Professor Branislava Gor, from Karlsruhe Institute of Technology, Institute for Applied Materials, Applied Material Physics. Please, Branislava.
Yeah, good morning, everybody. Yes, perfect. I can also see my slides, and you can hear me, correct?
Yes, correct.
Yeah, perfect. Yeah. It is a big pleasure for me to give a presentation about my recent research. The topic of my talk is formation of protective oxides on refractory metal-based materials. Therefore, we will talk about oxidation, corrosion, and protection of refractory materials. I will start with a brief introduction. Then we will talk about binary oxides and beyond binary oxides. I will then continue with the complex oxides, which may be regarded as protective in high entropy materials, and finally on other refractory systems. At the end of my presentation, I will sum up it and give a short outlook. Okay, let's get started. If we're talking about protection of refractory metals or in general metallic systems, we are talking about growth of oxides on metallic matrix, which separate the metal from the oxidizing atmosphere. In order to assess whether this oxide scale and this oxide is protective, we usually use different aspects such as thermodynamics and kinetics. On the right-hand side, you can see the so-called Ellingham-Richardson diagram. This is a very famous tool for us to assess the thermodynamic stability of oxides. As a rule of thumb, we say the lower the free energy of formation, the more thermodynamically stable is this oxide, and therefore the probability that this oxide is protective is higher. Here we can see a diagram which represents the parabolic oxidation constant, which is plotted versus temperature. And here, the lower the Kp value, the lower the growth rate of this particular oxide. In addition to thermodynamics and kinetics, we can use other issues which are important for us. For example, melting point of oxides. Again, as a rule of thumb, the higher the melting temperature of the particular oxide, the better. thermal expansion coefficient. Yeah, here we have to consider also the underlying matrix, and the mismatch between the thermal expansion coefficients between the oxide and the metal should be minimal. Peeling Bedworth ratio should be a little bit higher than unity. In this case, we can expect high protectiveness of this oxide. Besides, there are other aspects which can be decisive, considering the protection of the refractory metal-based materials. And if we have a closer look at this pretty big table, we have a number of oxides. We can state that only 3 of this long list, only 3 oxides can be protective, namely chromium oxide, aluminum oxide, and silicon oxide. Other oxides are regarded as non-protective due to various reasons. For example, phase transformation, cracking, faster growth rate, or in case of refractory metals, this is well known. Many of refractory oxides, they melt or evaporate at elevated temperatures, and this temperature limit could be very different. For example, in case of vanadium oxide, the melting process starts at 675 degrees C. So therefore, we have had only 3 options to protect refractory metal-based systems using 3 oxides: chromia, alumina, and silica. I think many of you know Per Kofstadt. This is the god, the scientific god in high temperature corrosion and oxidation. And this is one citation from his famous book. Diffusion rates in double oxides and spinel are often appreciably smaller than in single oxides, and protective scales on high-temperature oxidation-resistant alloys often consists of complex oxides. Many such oxides may be contemplated as the protective component. Indeed, if we have a look at this diagram, which shows the diffusion coefficient plotted versus temperature, we can clearly see, for example, that the diffusion rate of nickel and chromium in complex oxides, such as nickel chromium 204, the diffusion coefficients are lower in comparison to nickel in single oxide nickel oxide, and even chromium in chromium oxide. Therefore, complex oxides may be interesting and perspective in terms of a high temperature oxidation protectiveness. Yeah, which complex oxides do we know? Actually, a lot. Solid solution oxides such as corundum, chromium aluminum 203, or refractory metal-based oxides such as niobium, tantalum 205. We know also a lot of spinel oxides, such as I have already mentioned, nickel chromium 204. These oxides are pretty well understood and explored. However, we have a lot of other oxides such as rutile, tri-rutile, pseudobrookite, which are significantly less investigated. There are a lot of other complex oxides such as perovskite, ilmenite, and so on and so on, and also the high entropy oxides. However, the application of such complex oxides are mainly restricted to functional properties. And we are talking here about protective oxides which grow on structural materials. And therefore, yeah, we move on to the next part of my presentation, complex oxides in high entropy materials. Couple of years ago, we have developed a system, refractory metal-based system, which consists of 5 elements, namely tantalum, molybdenum, chromium, titanium, and aluminum. And we discovered that this high entropy alloy, that means we have the same amount of all elements in this high entropy alloy. In this case, we have five elements, and therefore the concentration of each element is 20 atomic percent. We discovered that this equiatomic high entropy alloy forms this pretty rarely encountered oxide chromium tantalum 04. A few words about the microstructure of this material. This alloy consists in general of three phases, depending on the temperature. At room temperature, the material consists of 2 phases, B2 matrix, and the Labes phase. And this phase appears here as a bright phase. Yeah, this phase which decorates grain boundaries in this material. At elevated temperatures, we have, instead of the ordered B2 matrix, the disordered A2 phase. Both are BCC. So we investigated mechanical properties, oxidation resistance, the microstructure stability, and other properties of this material. And the striking property was the high temperature oxidation resistance. We were very surprised that this equiatomic alloy, and it was really our first attempt, shows very, very high oxidation resistance, which is actually unusual for refractory metal-based alloys. Yeah, we know, and I have already mentioned that refractory metals, they possess extremely poor oxidation resistance because of the formation of either fast-growing oxides, such as niobium or tantalum pentoxide, or refractory metals build gaseous oxides which just evaporate. And so we compared the mass change of various refractory high entropy alloys after oxidation for 20 hours at 1000 degrees C in air, and we observed that our equiatomic alloy shows extremely low mass gain as compared to many refractory high entropy alloy systems. So we investigated the oxidation behavior qualitatively, and the results are shown here. We compared with a single crystal nickel-based superalloy, CMSX4, and you can clearly see that the nickel-based superalloy starts to melt at 1400 degrees C. This is actually not surprising. Surprising was the good oxidation behavior of our equiatomic high entropy alloy. Even at 1500 degrees C, we observed very, very sharp geometry, yeah, the contour of our sample. And this was already a sign that the oxide scales which grow on this material are pretty thin. We, of course, investigated the oxidation behavior also quantitatively. So, and here you can see the mass change, the surface-specific mass change as the function of time at different temperatures, at elevated temperatures. The result is clear. Even at 1500 degrees C, the mass change, the mass gain is very moderate. I have to add a very important information. We have also investigated the evaporation rate of molybdenum, in particular of molybdenum, because we know molybdenum forms gaseous oxides at temperatures above 800 degrees C, and our experimental finding was that we can actually neglect the evaporation of molybdenum, which is also very unusual because of a pretty high amount of refractory metals. Here we have tantalum and molybdenum as absolutely clear representatives of refractory metals. Sometimes chromium can be also regarded as refractory metal. So here on the right-hand side, we can see the cross-section of the oxidized sample. And here we found a lot of oxides. In particular, the complex oxide based on chromium and tantalum. Then we also found aluminum oxide, titanium, and chromium oxides. First, we were not aware about the protective properties of the complex oxides, and therefore we try to understand which oxide is actually responsible for this pretty good oxidation resistance. So therefore, we performed in-depth studies, including TEM studies, and we carried out one particular experiment. So first, we pre-oxidized our material at 1000 degrees C for 6 hours, and we found all these oxides. The outer scale consists of titania. This is bright gray scale. And then we found discontinuous alumina layer, and then the complex oxide. So we then removed this outer layer, including titania and alumina, leaving only pretty thin layer of the complex oxide. What you can see here, this bright face, this is the thin layer of the complex oxide, and below, yeah, here and here, we have a pretty pronounced zone of internal corrosion. Yeah, we have aluminum oxide and titanium nitrides, but it was for this experiment not actually relevant. So we removed this outer part of the oxide scale, and then we exposed this sample again to air at 1000 degrees C for the next 24 hours. And this is the result of this experiment. We found that, yeah, here we have again these two pictures and the schematic representation. The result was that the thickness of the chromium tantalate, yeah, this complex oxide, the oxide scale thickness increases, as well as the thickness of the zone of internal corrosion. Otherwise, we didn't observe any outer oxides, such as here titania and alumina. Our conclusion was that the chromium tantalate grows inward as a result of the oxygen inward diffusion, and exactly this oxide represents the barrier between the gas phase and the underlying substrate. In addition, we carried out a further experiment. So we wanted to know what is the original surface, and if we know the position of the original surface in the oxidized sample, we can also conclude which diffusion fluxes predominate and which diffusion fluxes actually contribute to the formation of the oxide scale, and in turn to the protectiveness of this material. So therefore, we milled a marker using the focused ion beam, using the gallium ions. And so we knew that the distance from the center of this marker to the surface is exactly 100 microns. Then we oxidized our sample with this focused ion beam marker, and again measured this 100 microns and found the original surface. And again, this is the
Sorry,
Hi.
Branislav, we don't hear you.
Check the internet connection, maybe.
Okay.
Yes, well.
Now, can you hear me?
Yeah, yes, I know. Yes, well.
Yeah. Should I continue or should I go one step back?
I think continue, please.
Yeah. Okay.
Yes.
So, yeah. Short summary of this, just of this slide. We performed two additional, two more or less elaborated experiments to understand the diffusion fluxes and in turn the oxidation mechanism, which can explain the good protectiveness of this equiatomic high entropy alloy. So the second experiment, I will continue with the second experiment. Yeah, we milled a marker using the focused ion beam, and therefore we knew the exact distance between this marker and the original surface. It was 100 microns. Then we oxidized this sample and found the original surface, which is marked here in this blue line. And our conclusion was therefore that all oxides which are located above the original surface grow as a result of the outward diffusion of metallic cations, whereby all the oxides which lie below the original interface, they represent the result of the inward oxygen diffusion. And therefore, the results of these two separate experiments they confirm each other, and they confirm our hypothesis that the chromium tantalate, this complex oxide with a rutile crystal structure, is responsible for the good oxidation resistance of the equiatomic refractory high entropy alloy. So then we asked ourselves, why is this oxide is actually protective? So we know we have to understand thermodynamics and kinetics. We performed very simple thermodynamic calculations to assess the standard free energy of formation of complex oxides, and we found that this chromium tantalate and other complex oxide, which was also found in the oxide scale, these two oxides, they are pretty thermodynamically stable. At least we can state that this complex oxide are they exhibit higher thermodynamic stability as compared to chromium oxide. And this was a very new and very promising finding. Then we moved to kinetics, and we plotted the kinetics data, in particular the logarithm of the mass change as a function of time, and we found the parabolic obedience, parabolic growth rate law. And we know if one oxide grows according to the parabolic rate law, that means we have solid state diffusion, which is a slow process. And all protective oxides, including chromia, alumina, and silica, they grow according to the parabolic rate law. So it was a very important finding. And finally, we compared the parabolic oxidation constant, Kp, as a function of time of our complex oxide with the well and widely accepted protective oxides such as chromia, alumina, and silica. And so, this is the main result. The complex oxide can be protective, and even more protective as compared to chromium oxide. This is the main observation. Then we had a closer look at this oxide, and actually we know that this is a rutile type crystal structure, and we also know that this oxide grows as a result of the inward oxygen diffusion. Therefore, we assume oxygen vacancies as the main defect in the crystal structure. Our hypothesis was, if we add specific elements with a higher valency, for example, here we can decrease the defect concentration of oxygen vacancies, and therefore we can then positively influence the oxidation rate. So we added tungsten and rhenium as the higher valency metals, and also copper as a low valency metal, just to test our hypothesis. And indeed, our hypothesis proves to be true. This is the undoped material after oxidation. This is the rhenium and tungsten doped material, and we can clearly see that the addition of small amounts of rhenium and tungsten leads to a significant improvement of the oxidation resistance. We observed thinner oxide scales, as well as thinner zones of internal corrosion, as we can see here. In case of copper, on the contrary, we found pretty thick oxide scales. I have, however, to mention that the effect of kappa on the microstructure was significant, and therefore it is not possible to explain the deterioration of the oxidation behavior just by the doping effect. So we assume also the effect of the effect on the microstructure. So we then oxidized our material in steam, yeah, in environments with the water vapor, because we know if we wanted to apply a material, for example, in gas turbines, we have to do with complex environments, including water vapor. And so we oxidized our aquatomic alloy in water vapor containing atmospheres. To our surprise, again, we didn't find our complex oxide based on chromium and tantalum. Instead, titanium tantalum oxides were found, and the oxidation behavior was found to be less protective as compared to air. Therefore, the formation of complex oxides is very sensitive to the alloy microstructure, but also the environmental conditions. And I would like to show you a couple of slides about other systems, including refractory metals. This is our this couple of slides show our recent investigations. We developed titanium-rich oxides based on the well-studied system. We performed thermodynamic calculations, and so we identified a couple of compositions which may be interesting and perspective from the mechanical point of view, and also oxidation resistance. So here you can see one alloy with this pretty complex chemical composition, and this alloy shows moderate plasticity even at room temperature. It should be emphasized that the aquatomic alloy is brittle up to 1000 degrees C because of the ordered matrix, ordered B2 matrix. In this case, we have the disordered A2 phase, and therefore, yeah, it was our hypothesis that the matrix should be more ductile. And indeed, we saw at least signs of plasticity in the compression test. With respect to oxidation, we observed the chromium titanium tantalum based oxide, and the oxidation resistance is actually, this is the oxidation resistance as compared to other titanium based alloys, and we can see, this is T1, T2, and T3. These are our materials, and we can see that oxidation resistance is indeed very perspective. Our alloys show superior oxidation resistance, and in case of the mechanical performance, we can clearly see that our materials are show really big prospect in the temperature range between 7 and 900 degrees C. So where the usual and common titanium-based alloys show clear degradation of the mechanical properties. And this is the last result. We investigated the oxidation behavior of chromium tantalum, very simple system, a binary system, and we also found the formation of the chromium tantalum oxide, which leads to the significant decrease in the specific mass change. Again, this result underscores the big potential of complex oxides which grow on refractory metal systems, and exactly this oxide, chromium and chromium tantalate and other derivatives, they consist themselves of refractory metals. And our message is that systems which contain chromium, tantalum, titanium, they can be protected by family-grown oxide scales. So I think I have no time anymore. So I have just a couple of slides which summarize the main properties of complex oxides. I will, I think, leave them, and I would like to ask questions.
Thank you very much for the interesting presentation. Any question for Professor Gore? Yes, please.
Okay. Professor Gore, thank you very much for your nice presentation. You showed us very nice result about high entropy metallic materials. But what do you think about the prospects of the high entropy ceramic materials? Maybe you saw in your scientific work in this side also.
To be honest, I have no experience with the ceramic materials, but the refractory metals, they built also a lot of, I would say, yes, silicides, aluminides, and so on. And therefore, I can really assume that also such materials can form protective oxides. Yeah, I think the fine microstructure can be decisive in this respect.
And the principle is the principle of oxidation resistance for, as you described in your presentation, for metallic materials will be the same for the high entropy ceramics. What do you think?
Yeah, I can really assume it because we have a lot of experience with the molybdenum-based materials, which include a lot of silicides. Yeah, and if we have a proper distribution of such silicides, with the high concentration of silicon, we saw that protective oxides can form. Therefore, we can try indeed transfer this concept, the formation of protective complex oxides also to the ceramic materials. We were just concentrated on metallic systems, but we can try also with ceramic materials.
Okay. We hope to do this together.
Yeah.
Thank you. Thank
You're
you
very
for your
welcome, Yuri.
answer. Thank you.
Dr. Vasily, please, your question.
Bronislava, good morning, and thank
Good
you very
morning.
much for consistently excellent talks from you. Another consistently excellent talk from you. I wanted to ask about these mixed oxides or complex oxides, as you call them. I just wonder what is the comparison with the pure oxides? For example, you mentioned that chromia is also an excellent oxidation resistant, not resistant, but an oxide providing resistance. So what happens? Does tantalum just dilutes chromium sublatis, or what are the possible mechanisms that that these complex oxides work perhaps even better than the pure?
This is a good question. To be honest, I don't have any definite answer because we don't have experimental proof. I can just talk about hypotheses. And what we saw that this complex oxide, we are talking just about chromium, tantalum, also titanium-based alloys. This oxide is thermodynamically more stable than chromium oxide. Here, for example, we can see the chromium oxide, and below the very dense and continuous chromia layer, the chromium tantalum oxide forms. That means this oxide is thermodynamically more stable, requires less oxygen. And the protective oxide should lie exactly on the metal. We want to protect our metal. Therefore, the stability is important, and the growth rate. We don't know what is the exact defect structure. What is the thermal stability? We plan to investigate all these properties in a big joint project, and hopefully that we will succeed, and finally we will discover step by step all the properties, because it's just the experimental finding which is positive, but we have to generate the solid knowledge with different aspects, and then we can explain, and hopefully we can transfer also the formation of this new oxide to other systems. In general, it's only 3 oxides, and in fact only 2 which can protect metallic systems, chromia and alumina, and we propose a third, the complex oxide, which can be better than chromium oxide. I would and I can also add that the most of high temperature materials, they are protected by chromium oxide, and if we propose an oxide which is better than chromium oxide, this would be really a huge step forward.
Thank you. Bronislava, if I may, one really small clarification on the thermodynamic stability. What exactly do you mean here? Is it the partial Gibbs energy, or Because the intuition says that chromium oxide should have perhaps lower Gibbs energy, no?
No. Then I'll go to the Ellingham-Richardson diagram. Yeah, to the Ellingham-Richardson diagram, we are talking about the Gibbs energy of formation, and from this Gibbs energy of formation, we can calculate the equilibrium oxygen partial pressure. Yeah, this scale.
Mm-hmm.
Yeah, from the delta G0, we can calculate the equilibrium oxygen partial pressure. That means the minimal oxygen content which is required for the formation of this particular oxide. And here, our chromium is here. Yeah, and the chromium tantalate will lie between the chromium and tantalum. Tantalum is not here, but it's somewhere here. And therefore, chromium tantalate requires less oxygen for the formation than chromium oxide. And in fact, chromium tantalate, this is the product of the reaction between chromium oxide and tantalum oxide. But if we find this oxide below the chromium oxide, that means this oxide is more stable thermodynamically.
Okay, thank you. That requires further look from me. Thank you very much.
You're welcome.
The last question, please.
Yeah, thank you for your presentation. One short question. Did you investigate the influence of amount rhenium and tungsten when you use it to dope your tantalum, molybdenum, chromium, titanium alloy? Yeah.
Yes, I'll go to this slide. We add 3 atomic percent of here rhenium and tungsten to the equiatomic material. Yeah, and our hypothesis was that we will reduce the concentration of oxygen vacancies. So therefore, we will have less paths for diffusion for oxygen, and therefore the growth rate would be lower.
Yeah, I mean here, why 3%? Why 3 atomic percent? It was a guess or from your output or from your hypothesis? Or maybe you make some experiments and 3% gave the best result?
No, it was just one attempt. Why 3 atomic percent? We wanted to have on the one side, we wanted to have prominent doping effect. That means the dissolution of these elements in the scale. On the other hand, we didn't want to influence significantly the microstructure. Yeah, because in this case, we would have 2 different aspects: microstructure effect and doping. And we wanted to explain the differences by the doping effect.
Okay, so as I understood, further to find optimum value, it's need further investigation, yeah?
Of course, yeah.
Yeah, okay, thank you.
Thank you for your question.
Thank you, Bronislaw, one more time. Good luck in your research, and all of us hope to see you in Kiev better personally at our conference.
Of
Thank
course,
you one more.
of course. Yeah,
Yes.
thank you very much. Good luck.
Thank you. Good luck. Well, continue our work. The next presentation will be done by Mikhailo Turchanin. Is there Mikhailo Turchanin? Online, yes? Please. Is in connected?
Good day. I suppose
please.
that Professor Turchanin is busy now, so I will replace him and show our presentation, if you please. Okay?
Okay. What your name, please?
Pavlo Agrawal. I'm represent our team of
Yes.
investigations.
Thank you. Please start your presentation.
So, dear colleagues, I will present our report on the thermodynamic aspects of interactions between components in liquid copper, cobalt, nickel, zirconium, hafnium, alloys. And alloys of these systems is the basis for creating an important new class of materials, which has the name high energetic structural materials, ESMS. This new type of material combines structural strength and the ability to rapidly change, to rapidly release chemical energy under conditions that cause sorry, I am switch to show. Okay, sorry. Under conditions that cause the mechanical failure. Example of such investigation are shown here. Today there are known several types of such materials, and main of them are listed here. These materials can find their application in military fields as kinetic penetrators, reactive fragments, bullets, and armor. Our special attention is drawn by high energetic bulk metallic glasses. Let's consider more thoroughly properties of such materials. For example, here are shown results of investigation of bulk metallic glass, which is conducted by Saini. This material combines the several properties which is important for the ammunition, such as zero plasticity, localized deformation, self-sharpened chiseled nose forms for enhanced penetration, explosive outfit, and ignition which occurs in air. Also, the high density is typical for ASMBMG connected with the high hafnium content. Here also shown example of experimental results of ballistic test performed on samples of the zirconium-based BMG alloys. As we can see, these alloys prove their potential to use as kinetic penetrators for such type of ammunition. So the hafnium-based bulk metallic amorphous alloys with high energy characteristic are new promising materials for developing kinetic penetrators for new ammunition. The objective of our work is to investigate thermodynamic aspects of the interaction between components in liquid copper, cobalt, nickel, zirconium, hafnium alloys as a basis for developing high energetic amorphous alloys. Tasks of the work are: first, experimental study of the mixing enthalpy in the liquid copper, zirconium, hafnium, cobalt, zirconium, hafnium, and nickel, zirconium, hafnium alloys. Second, modeling the temperature composition dependence of the thermodynamic properties of the liquid investigated alloys using the associated solution model. Third, development of thermodynamic database for the copper, cobalt, nickel, zirconium, hafnium system based on interaction parameters of boundary, binary, and ternary systems. Fourth, usage of the relevant thermodynamic database for the calculation of thermodynamic properties of multi-component liquid areas in the framework of associated solution model. Fifth, analysis of composition and temperature dependence of the thermodynamic mixing functions such as enthalpy, excess entropy, excess Gibbs energy, and Gibbs energy of the liquid areas for the quinary system and for bounding ternary and quaternary systems. So let's look at the phase diagram and thermodynamic properties of systems with strong interaction of components. The main features for the thermodynamic properties of the liquid LS are significant negative values of the integral mixing enthalpy, negative deviations from Raoult's law for the thermodynamic activity of components, phase diagrams characterized by deep eutectics, which is typical for the systems favorable to formation of amorphous areas. All this allows us to suppose localization of chemical bonds and emergence of chemical short-range order in liquid areas, which closely relates with formation of associates, and this led us to use the associate solution model. Here we presented the structure of Gibbs energy model in the case of the ternary liquid areas of two binary systems with preferable interaction between different types of atoms in the liquid areas are described using associate solution model, whose composition can be described by the mass action law. The last one binary system with a weak interaction of component described using the Rayleigh-Kister polynomial. The last term represents the possible ternary interaction, and for the description are used Rayleigh-Kister-Muggiano equation. To perform thermodynamic calculations for liquid areas of multi-component systems, we must develop the database which contains information on boundary, binary, and ternary systems. Today, thermodynamic parameters for 10 binary systems are well known. For the boundary ternary systems, we have only information about 7 ternary alloys. As consequence, we must investigate the thermodynamic properties for the liquid copper zirconium hafnium, cobalt zirconium hafnium, nickel zirconium hafnium alloys. Examples of such investigation are performed in our laboratory is shown at this slide. The partial enthalpies of zirconium and hafnium for the liquid copper zirconium hafnium alloys at 1873 kelvins are investigated along the sections using our high temperature calorimeter. Obtained results are shown here by red circles. These data are described by polynomial models, and this function was used to calculate integral enthalpy of mixing by integrating the Gibbs Duhem equation along sections. Obtained values was used to describe the integral enthalpy of mixing in the entire composition range using the Rayleigh-Kister-Muggiano equation. The negative values of this function as a result of calculation are realized to the copper hafnium and copper zirconium systems, indicating that appropriate interactions plays dominant role in the energetics of liquid alloy formation. These experimental results shown by red lines are used to model thermodynamic properties of liquid alloys in the frameworks of the associate solution model. Results of calculation are shown here by blue lines. Experimental results are shown by red lines. As we see, the calculation results describes well the experimental results, and so we can use these obtained model parameters to describe other thermodynamic properties. The same investigations are performed for the other two systems as cobalt zirconium hafnium and nickel zirconium hafnium. As a consequence, we used obtained data to model in the framework of the associated solution model the thermodynamic properties of these alloys, and at this slide we show the calculated thermodynamic properties of liquid alloys of these ternary systems at 1873 kelvins. These calculations also performed at other temperatures, including the temperature 800 kelvins. The comparison of the obtained results shows that the temperature composition dependence of the thermodynamic properties of liquid alloys in the range of temperature from 800 to 1873 kelvins consists from the negative deviations that grown from ideal behavior with decreasing temperature. The obtained model parameters are used to complete the database, which is used to calculate thermodynamic properties of multi-component liquid alloys. This slide presents the results of calculation for the four-component liquid copper, cobalt, nickel, hafnium system at 1873 kelvins. This slide shows the thermodynamic mixing functions of ternary melts of boundary systems assembled in a form corresponding to unfolded composition tetrahedron. The negative values of the thermodynamic properties are in the most part of the composition tetrahedron. To understand how thermodynamic mixing functions behave inside composition tetrahedra, their values are shown along the section connecting pure elements with the opposite equiatomic ternary compositions. The four-component equiatomic composition are shown by a vertical line. The composition codes of the thermodynamic properties in the calculated sections are different, and in the section copper, cobalt, nickel to hafnium section, the minimum of the Gibbs energy and integral mixing enthalpy is around the center. The same calculations are performed for the liquid oils of the quinary copper, cobalt, nickel, zirconium, hafnium system at 1873 kelvins. The results are shown in the form of the sections which connect pure elements with the equiatomic four-component compositions. Equiatomic five-component compositions also shown by vertical lines. The maximum of thermodynamic stability of liquid multi-component alloys is observed in the transatomic region. The same calculations in the framework of the associated solution model were conducted for the quinary equiatomic liquid alloys of the copper, iron, cobalt, nickel, titanium, zirconium, hafnium system at two temperatures, 1873 and 1800 kelvins. The relative contribution of the ideal Gibbs energy in the Gibbs energy for equiatomic liquid alloys decreased from 68 to 80% at 1873 kelvins to 20-40% at 800 kelvins, but remained noticeable and makes a significant contribution to their thermodynamic stability. And special attention must be devoted to hafnium-rich alloys. There is presented calculation results of thermodynamic mixing functions for liquid alloys along the section connecting pure hafnium with copper, cobalt, nickel, zirconium equiatomic alloy. These calculations are performed at two temperatures, 1873 kelvins and 800 kelvins. The maximum thermodynamic stability of liquid multi-component alloys at low temperature is observed for the composition with 31% of hafnium. Also here presented calculation results for liquid alloys along section connecting copper, cobalt, nickel, zirconium with copper, cobalt, nickel, hafnium section. These calculations are also performed at two temperatures along the this section, the thermodynamic mixing function shows a smooth compositional cause. All these results, which is shown here, points to the conclusion that with decreasing temperature, the thermodynamic stability of liquid multi-component alloys increases, and the enthalpy factor begins to play a decisive role. So we can make some conclusions. First, liquid alloys of the copper, cobalt, nickel, zirconium, hafnium system are the parent material for producing high energetic amorphous alloys, so their thermodynamic properties require experimental study and theoretical modeling. Second, at the first time the mixing enthalpy of liquid alloys of the copper zirconium hafnium, cobalt zirconium hafnium, and nickel zirconium hafnium systems were studied calorimetrically at 1873 kelvins. The native values of the mixing enthalpies were established, and the dominant role of strong copper zirconium, copper hafnium, cobalt zirconium, cobalt hafnium, nickel zirconium, and nickel hafnium pair interactions was demonstrated. Third, the thermodynamic mixing functions of the ternary investigated liquid alloys were modeled within the framework of the associated solution model. The temperature composition dependence of the integral enthalpy, the excess mixing entropy, the excess Gibbs energy, and the Gibbs energy in the range of 800 to 1873 kelvins was determined. It was shown that net deviations from the ideal behavior increase with decreasing temperature. Fourth, the database for the excess Gibbs energy of these quinary liquid alloys has been supplemented with new experimental results, and the thermodynamic mixing functions for multi-component glass forming systems were calculated. The calculation results show that the glass forming liquid alloys exhibit high thermodynamic stability over a wide temperature range from equilibrium state insignificant under Kuhn. The contribution of ideal part of Gibbs energy for quaternary and quinary equiatomic liquid alloys at 1873 kelvins varies within the range of 60 to 80%. At 800 kelvins, the ideal contribution decreases to 20-40%, and the integral mixing enthalpy gives the main contribution to the negative values of the Gibbs energy of mixing. Fifth, a wide composition range in the copper, cobalt, nickel, zirconium to copper, cobalt, nickel, hafnium section, the thermodynamic stability of supercooled liquid alloys exhibit a nice flat minimum at high hafnium content. The maximum thermodynamic stability at 800 Kelvin is observed in the copper, cobalt, nickel, zirconium to hafnium section for the composition with 31% of hafnium. Thank you very much for your attention. Please, your questions.
Thank you very much for the interesting report. Any question to Pavlo? From your permission, I'd like to know, maybe you have any information about structure of this high entropy alloys you studied in liquid state. I mean atomic short range order. Maybe you have some information.
No, today we only on the first stage of our investigation. We only performed the thermodynamic calculations, prepare our database, and the calculation of the chemical short order in the liquid multi-component alloys will be the next step. And at this step, we will perform also evaluation of the possible amorphization range. And this work goes to the third stage, then which is more complicated, and maybe we obtain also experimental some results on the these amorphous alloys.
Thanks. It is a very interesting moment, and I hope you will report your results in the next our conference. Thank you.
Thank you.
Thank you one more time. And the next presentation at our conference will be done by Artem Yeremenko. Please.
Good morning, dear attendees. Today, I would like to present the results of our research devoted to effect of heat treatment on the structure and mechanical properties of Inconel 718, alloy produced by additive manufacturing in the cast and wrought condition. Nickel-based superalloys occupy a leading position among materials used under conditions of high temperature, significant mechanical loads, and aggressive environments. The global market of these alloys is projected to grow by 8% annually. They are widely used in the aerospace and energy industries, particularly for manufacturing gas turbines and pump components. The relevance of the study, these materials, is driven by the continuously increasing requirements for the heat resistance, durability, and reliability, especially under elevated temperatures and cycle loading conditions. In this context, special attention is drawn to the Inconel 718, which combines high mechanical properties, corrosion resistance, and manufacturability, including good durability. In recent years, a number of studies on manufacturing Inconel 718 components using additive methods has increased. This is because additive manufacturing enables the production of parts with complex geometry and reduced weight for aerospace equipment. However, additive manufacturing significantly affects the structure and properties of the products. Additive manufacturing and casting form different initial microstructure characterized by different in-grain size, degree of alloying, element segregation, presence of defects. Therefore, standard heat treatment regimes developed by traditional technologies do not provide an optimal combination of properties for additive manufacturing materials. In this, for this research, we used two series of samples. First series of samples were produced by selective laser melting, aka SLM. They were produced by scanning parameters like speed of scanning 50-100 millimeters per second, layer thickness of 25 micrometers, and height spacing 150 micrometers. Also, producing were made in an atmosphere of argon. For compressions, samples obtained by electroslag remelting were used. They were heated in a resistance furnace to 150 degrees Celsius and held for an hour. After that, forging deformation with a slight reduction for amount 3 millimeters was performed until the end of the forging temperature range of 750 degrees was reached. The billet was then returned to the furnace, reheated to 1050 Hz, and held for 10 minutes. After which, the deformation and reheating cycle were repeated until the billet cross-section dimension reached approximately 12 millimeters per 12 millimeters. After that, forged sample was held to the furnace until reheated again to 1050 Hz. The first regime was annealing. It was held by 1000 Hz for 2 hours and then cooled with furnace. Second regime was chosen quenching, which was performed by 1000 Hz for 1 hour and air cooling. And the third regime was chosen quenching plus aging. It was also like in quenching performed by 1000 Hz for 1 hour with air cooling, but after that it was again reheated for 720 Grados for 8 hours, and then cool with furnace, and then reheated again for 620 Grados for 8 hours, and then cooled with furnace again. The chemical composition of the two series of samples was determined using X-ray fluorescent analysis. This showed that Inconel 718 has a typical composition for this alloy with the large amount of nickel, chrome, and ferrum. In the initial state, the structure is characterized by pronounced bending and directionality, resulting from plastic deformation. Elongated grains and deformation bands oriented in the processing direction and absorbed. After annealing, significant microstructural rearrangement occurs that deformation texture decreases, and the structure requires a more equilibrium appearance. After quenching, the structure becomes more dispersed and uniform due to rapid cooling. A supersaturated solid solution is formed. After quenching followed by aging, the structure becomes more stable and ordered. Some leveling of the microstructure and reduction in contact between individual regions and are observed. Also, diffraction showed that in all states we have gamma BCC structure of nickel. The initial states of the structure characterized by in SLM. The initial state, the structure is characterized by alongside node pool traces and layer structure typical for the SLM process. Surface irregularities, isolated pores, and defects formed due to incomplete fusion of the mold pools. After annealing, the structure becomes more ordered. Partial smoothing of mold pool traces are reduction in layer visibility are observed. At the same time, an ordered structure in the form alongside grains or subgrains appears, associated with recovery and partial recrystallization process. After quenching, the microstructure appears more uniform. Also, some defects such as pores and micro cracks remains. The surface texture becomes less pronounced, indicates the formation of a supersaturated solid solution. After quenching followed by aging, the structure becomes more dispersed and homogeneous. A reduction in surface defects and formation of a more stable microstructure are observed. In the initial results of microhardness shown by the graph, in the initial state, cast-deformed samples exhibit higher micro-hardness, something around 460 HV. This might be related to strain hardened and more stabilized structure after plastic deformation. After annealing, SLM samples up to micro-hardness up to 521 HV is observed, which is the highest value among all states. This might be due to partial stabilization of the structure, stress relaxation, and possibly of the initial precipitation of the strengthening phase. After quenching, micro-hardness decreases in both cases and amounts to 370 and 324 for deformed sample. This is associated with the formation of supersaturated solid solution without precipitation of strengthening phases, like gamma prime phases. After quenching, followed by aging, a repeated increase in micro-hardness is observed, up to 506 for SLM and 400 for HV. For cast-deformed samples, this is caused by intensity precipitation of coherent gamma prime phases, which effectively hinder this distillation movement. Conclusions were preserved during the report, so please allow me not to read it aloud.
Thank you very much. Any question to the reporter? Yes, please.
My question is about the mechanical properties. Did you measure only the micro-hardness for these alloys? But what about the strengths?
Yes, thank you for question. Yes, only micro-hardness for this. Maybe we will measure some different properties in the future.
But maybe fracture toughness using indentational technique. Also not only micro-hardness.
Only micro-hardness, sorry.
Okay, thank you.
More question, please. As I think you got alloy by this method, yes?
Yes, some results show that annealing SLM samples have very big, very high measurement for hardness, micro-hardness.
And what size of your sample can you produce by this technique?
SLM has some bonders for this, such as size of printer.
Yes, yes, of course. But 1 centimeter, 10 centimeter.
For printers that we used, maybe 20 centimeters, maybe. Like
20 centimeters. Thank you. More question. Thank you one more time.
And now I'd like to invite Professor Alexander Ruch, head of the Department of Structure and Properties of Solid Solution of the Kurdymov Institute of Metal Physics of the National Academy of Science of Ukraine, with the presentation Metal Injection Molding of Infanel 718 components, challenges, and solutions. Professor Root, the floor is yours.
Thank you. Dear colleagues, my presentation devoted to investigation metal injection modeling of Inconel 718 components, challenges and solution. A couple of words about this technology and why it is very important now. An important issue on industrial manufacturing metal articles and components is cost performance dilemma, achievement of sufficiently high characteristics of final product and their reduced cost. As excessive cost of nickel alloy, forces development of advanced cost efficient manufacturing technologies for production products of their base. One of them is additive technology. We heard presentation before my report. Really, what is it? Metal injection. Metal injection molding (MEM) technology offers a viable alternative to conventional technologies for near net shape fabricating metal components by integrating thermoplastic injection molding with polymer with powder metallurgy principles. The MEM approach uses blends of metal powders and organic binders as starting materials. Which are compacted into preform or desirable shape. As following the processing stage, the organic binder should be evacuated from the MEM preform, the binding stage so-called, while compacted metal powder retains original shape of the preform and subjected to sintering, thus forming final sintering products of desirable shape. Really, this technology is just very bright used in technology, but practically work with steels, with copper alloys, very seldom with titanium alloys, and practically no parts made by this technology from nickel super alloys. So this we try to implement this technology for obtaining some detail, namely blades, turbine blades from nickel-based alloy, namely Inconel 718. As starting material, we used commercial gas atomized powder. With size 10-20 microns, and also as binder we use polymem. It is commercial trade mark. So spherical Inconel 718 alloy powder was used, the polymem binder, to fabricate feedstock granules 3-4 millimeter in size. Following MEM technique, the feedstock were heated to 180-200 centigrade. and after this, the mixed the blender was compacted by pressure about 100 MPa into preforms using molds, which shapes corresponded to various turbine blades. This one. The debinding procedure was performed in two stages as a rule. The first one, during the first debinding stage, the green MIM compacts preforms were washed in hot water, about 70 centigrade, for 1 to 2 days to evacuate water-soluble components of the binder, paraffin, so-called. For the second stage, the compacts were slowly heated in vacuum to 800 centigrade and exposed for 1-2 hours to remove residual polyamine binder components. After the second debinding stage, all powder compacts were heated at a rate of 5 Kelvin per minute for sintering up to the temperature to 1250 centigrade, which holding times of 2-4 hours. Two sintering options were tested, vacuum or argon atmosphere, in vacuum or argon atmosphere. The microstructure of MIM compacts are characterized by relatively dense and uniform packing of powders. The organic binder filled the residual space between powder particles without voids. Investigations of powder surface after debinding completion, heated up to 500 centigrades, revealed clean surface of all studied powder types. However, although binder remains were not remnants were not observed using SEM microscopy, thin surface film may still be present on the powders, affecting the further development on the sintering stage. So we obtain some preforms of turbine blades produced in argon and vacuum and in vacuum. Further sintering condition adjustment involves selecting the appropriate sintering atmospheres, vacuum or inert gas, as I said. Debinding in vacuum appeared more advantage in comparison with argon atmosphere. This because binder has possibility, better possibility to leave the preform. This process left the powder surface nearly clean, with only minor contamination from binder decomposition product. However, vacuum sintering at temperature above 1000 centigrade leads to significant evaporation of aluminium from preform. As a result, alloy products sintering in a vacuum showed reduced levels of these elements at the surface and in subsurface layers, aluminium and chrome, I'd like to say. For example, the chromium content on the surface of Inconel 712 products decreased in 2 times, from 20% to 10%. but sintering in the argon atmosphere at temperature above 1000 centigrade remains the chemical composition practically the same as starting material. Therefore, argon atmosphere during pre-sintering and sintering stage is preferable for Inconel 718. Sintering process was performed at temperature at 1230-50 centigrade under argon atmosphere, and this mode is recommended for production details from Inconel materials. Conducted X-ray analysis testify presence gamma phase and gamma strich and gamma 2 primes in the sample. Mechanical test show that obtained material possesses good mechanical properties. Stress strain is about 8 MPa, 800 MPa, and we propose two stage of sintering process. The first one vacuum debinding, then sintering in vacuum argon, then aging, and thermo processing. So at our experiment, MIM technology was successfully used for cost-efficient manufacturing gas turbine blades of Inconel 718 alloy. The regimes for debinding on Inconel plus polymim powder feedstock were developed, providing completed binder evacuation. The developing sintering and heat treatment regimes promote preservation of shape and integrity of MIM blank, while nearly dense sintered microstructure and desirable set of mechanical characteristics were achieved. Thank you for your attention.
Thank you for your presentation. I have the question. What do you think? What is the main advantages of the MIM process against the 3D printing?
Yes. Really, MIM process is just hard in formation of elaboration, technology elaboration. But if it has done, the production is very, very cheap. It can be produced very quick in a big quantity.
Mm-hmm. Very good productivity.
Yes, very good productivity
of this process. And next question, as I saw in your presentation, you use mostly the spherical powder for the MIM process. Is it needed, or you can use not only spherical powder? What is the main purpose to use spherical?
We try to use not only spherical particles, namely dehydrated titanium powders, not spherical shape.
It's quite brittle.
I think it is possible, but titanium and the superalloy are very hard for this technology, and we should work very hard.
Okay, and last question. I saw the powders was with not very narrow particle size. And what was the particle size you need for this process?
20-30 microns.
20-30 microns. Yeah. Okay, thank you. Thank you.
Thank you, Professor Rudd, for such a great presentation. And now we have a time for a coffee break, about 20 minutes, and after it, we will have a poster session of our conference. Thank you.
Translation. Yeah, colleagues, we continue our work and starting poster session. Please, the first poster. You? Please.
Traditional alloys are reaching the limits of their capabilities, which may relevant to such function materials as high entropy alloy. The relevance of the study is to determine the optional boron concentration to increase the wear resistance of the alloy. The aim of the work is to study structure and phase composition of the high entropy alloys aluminum, chrome, titanium, vanadium, bore, and establish the features of its structure, formation, and phase composition. Microstructure studies have shown that with increasing mechanical alloys, time particularly becomes smaller and their morphology change. Initially, large agglomerations are formed due to cold welding, but further processing contributes to the fragmentation and more uniform mixing of components. As a result, we obtain a more homogenical fine-grained structure with compact particle and uniform distribution of elements. X-ray phase analysis has established that during mechanical alloying of the power mixture and aluminum, chrome, titanium, vanadium, bore with a predominantly body-centered cubic crystal, let's see, gradually form. Increasing the MA time leads to the disappearance of individual initial phases and the formation of solid solution, which indicated intensive mixing of elements and stabilization of the alloy structure and a small number of intermetallic phases. The study of structure and phase composition of the aluminum, chrome, titanium, vanadium, bore made it possible to establish the future of its treatment and dense mixing of components, particular grinding, and the formation of more homogenic and fine-grained structure occur. X-ray phase analysis established the formation of solid solution with the formation of predominantly BCC crystal lattice and a smaller amount of secondary phase. They obtained data characteristic the main regulars of the formation of the structure and phase composition of aluminum, chrome, titanium, vanadium. That's all.
Thank you. Any question?
Yes, small question. Investigate did the boron create the traces with like borates with other metals?
Yes, it's make borates phase. It's like 2 hours and more.
2 hours and more. After that, you create borates and you see.
Yes.
Okay, thank you.
Thank you. Good luck in your study. The next one. Yeah, please.
Good afternoon. I would like to represent our subject of our institute. It's Physico-Technological Institute Metals of Alloys, National Academy of Science. And the subject of this poster, the effect of heat treatment on the properties of high entropy alloys of 2 systems. Iron nickel chromium kappa manganese and iron nickel chromium kappa aluminum, and both of systems contain carbon. So what is the object of this study? So we usually high entropy alloys was studied and is shown in the literature in SK state. Not so many work devoted to homogenization and annealing heat treatment of of high entropy alloys. So in this work, we studied homogenization of these two systems and study their before and after homogenization. We studied their structure and some properties. So we prepared using of this alloys. We prepared using induction, special designed induction furnace and in open air, but with argon flow. And we used some common materials, some high-grade pure metals, and also ligatures, cast iron, and stainless steel for preparation. So our result is so we use X-ray diffraction and optic electron microscopy to discover the structure. So before annealing, for example, system containing aluminum consists of several phases. This is a matrix and dendrites. And also this one is carbides. Complex carbides is containing iron and chromium carbides. In case of manganese system, this also it's have dendrites and matrix space. So after annealing, in case of this manganese containing system, dendrite grows, have grown, and interdendritic space decrease. In case of aluminum containing system, actually dendrites like disappear and increase eutetic structure. So aluminum, this is aluminum containing system X-ray diffraction. It consists of as I said, several phases. One of them is face-centered cubic structure, face-centered cubic, and second base-centered cubic structure, and some diffraction. No, and also complex carbide. So what we can say about hardness before and after annealing in case of system manganese containing system, hardness like decrease, no, mainly decrease. And we think this is due to homogenization and some dissolution on non-equilibric phases. And in case of aluminum, no, maybe for manganese system, it's increase, and for aluminum system, it's some decrease. So what application of our material, of our materials? So we, no, I won't say this is not included in this poster, but before we studied aluminum containing system, and it was good heat resistant material. So this is maybe can be used for heat resistance parts of devices. And in case of manganese containing system, no, I think this is for structural application. It should be good material. So the presentation is over. Thank you very much for attention.
Thank you. Thank you. Colleagues, any question?
No question.
No question.
I have a small question. What about this alloy? Why after annealing it have increased micro hardness value?
No, so as I said, this is increased, yes, for this system. And in this is, you mean this, why increased? So I think, so we studied several compositions. So we like smelled different, no, same system, but composition was a little bit different. I think due to fluctuation of composition in the alloy.
Homogenization maybe.
Or maybe not enough homogenization.
What does it mean, water quenching? Sorry.
Water quenching. So yes, so this was and one of them was after water questions, закалка.
Quenching.
Да, quenching, water quenching,
Okay.
закалка. Mhm.
What about plasticity of
Plasticity. No, this alloy contain aluminium and base-centered cubic phase.
Mhm.
So this is like хрупкая.
Brittle.
Да. And in case of more plastic, manganese containing, so up to if for elongation about 40%. Yes.
Thank you. Thank you. This next presentation will be done by Maxim Naumenko.
Yeah.
Please.
So the object of this work to investigate evolution of structural phase composition and mechanical properties upon introduction of significant amount of boron. The alloys were prepared by arc melting in argon atmosphere with multiple elements to ensure homogeneity. Phase composition was determined by fraction. Then it was studied by scanning electron microscopy with EDS analysis. Mechanical properties were evaluated by Vickers microhardness and instrumented indentation. When avoiding the counteralloy with tungsten, the hardness increases sharply, but the modulus practically does not change. The increase in hardness is explained by the change in the phase composition of the alloy, as the formation of hard to mu phase occurs in the alloy. The introduction of boron causes the formation of three types of borides in the ferrum cobalt nickel manganese chrom tungsten boron alloy, which leads to a sharp increase in both hardness and modulus. When replacing manganese with molybdenum in the ferrum cobalt nickel manganese chrom tungsten alloy, a simultaneous increase is observed in both hardness due to increase in the fraction of mu phase, and modulus due to increase in the share of high modulus elements. Additional alloying with boron promotes further sharp increases in the physical and mechanical characteristics of the ferrum cobalt nickel chrom molybdenum tungsten bore alloy, which are the highest among all the alloy investigated in the work, which is associated with formation of large amount of various types of borate phase. Thank you for attention.
Thank you. Any question, please? How do you produce your high entropy alloy?
We produce with arc melting
Mechanical alloy?
Arc melting in argon atmosphere.
Melting in argon atmosphere. Yes. At equipment at your faculty?
I'm a PhD.
Furnace.
In my faculty.
Yes. Thank you. Thank you.
So, if
Yes.
I question, homogeneity of the
We're melting multiple types to homogeneity.
Yeah, but did you check afterwards? How did you check? I mean, the high entropy alloy, if we are speaking about alloy, it should be a complete solution. Is it correct? Any elemental maps or something like that?
Yes, we do in scanning electron microscopy elemental map.
And it's
Yes.
a good solution. Yeah.
It's good solution.
Regular.
Right.
Thank you.
Thanks. Thank you. Success in your research. Yes. Next presentation will be done by Olena Makarенко.
Dear colleagues, let me introduce you attention my topic on them comparative analysis of methods for determining the specific surface area of reduced nickel powders. Now our work was to conduct a comparative analysis of specific surface area measurements using instruments based on different generation and methodological principles. We used a dynamic thermal desorption methods of nitrogen on an MPP2 sorbometer and a static volumetric bed method. Object of study presents of our poster and the results show that our results is one moment, please. It was established at the specific surface area of sample 1 determined by OPP is 0.8 square microgram and our conclusions, the lower SA values in the final fraction, simple 2, are explained by the increased temperature and the duration of reduction, which leads to active fusion bonding of the reduced particles of each other. The disparity between the results of different methods absolute range from 9 to 16%. The consistency of the trends recorded by both instruments confirms the high reliability of the powder characterization performed. Thank you for your attention.
Thank you, thank you. Equipment. I'm sorry, Alina. One small. This equipment, it is in your institute, or it will done?
Можна я українською відповім?
At your institute or no?
One is our, two no.
This one is your institute?
Our institute, two no. No. This is
Yes.
Ні, колега Ольга Чудінович in Польща нам.
In Pольща, yes. Thank you.
Дякую. Thank you.
Yes. Next presentation.
Good afternoon, everyone. I'm Yaroslava Martinenko. I am a student, and today I would like to present our research of the effect of arc melting parameters and mechanical alloying of the chemical homogeneity of GSK nickel-based superalloy for additive manufacturing feedstock. Our aim, the study investigates the effect of processing parameters like current, arc current and preliminary mechanical alloying on the elemental distribution in the GSK nickel-based superalloy to evaluate the efficiency of achieving chemical homogeneity for additive manufacturing feedstock. Our methods we produced by arc melting in an argon atmosphere at current of 165 to 180 amperes, as well as through a combined route, including preliminary mechanical alloying in a planetary mill up to 10 hours and speed 350 RPM, followed by the arc remelting at current up to 300 amperes. The chemical composition and its spatial distribution were analyzed using energy dispersive spectroscopy. Yes, the most significant chemical heterogeneity of GSK alloy is recorded partially at the microstructure level and is directly associated with the segregation of refractory elements such as molybdenum and tungsten. Traditional arc melting results in pronounced microstructural heterogeneity, which can't be completely eliminated even by increasing the arc current from 168 amperes to 180 amperes. And this only slightly improves uniformity. Yes, and emulsing provides an acceptable average composition of the JSK alloy, but result in microscale heterogeneity with small depth in the tungsten and particle depletion of aluminum and titanium. In contrast, the combined route with preliminary mechanical alloys promotes enhanced with mixing efficiency and a more uniform elements distribution. Also, aluminum and titanium depletion still occurs, making this approach promising for producing feedstock for subsequent atomization and additive manufacturing. Thank you for your attention.
Thank you. Any question, please? Very small, very, very small. Aim using, what is aim? Using mechanical alloying after production of spherical particles.
To do the best segregation in the metal that and chemical structure.
Thank you.
Yes, thank you.
Потом же их нельзя использовать. Ну, как помолол, это ж не... Ну, ладно, well. Next. Да. Please, your name, please.
My name is Sergei Kuleshov, and I presented from Vernadsky Institute of General and Inorganic Chemistry. And some of my co-authors are from China. It's Sergei Devyatkin, Petya Yang, and Rupen Li.
This study investigates the feasibility of electrodeposition of refractory titanium boron compounds from low temperature imidazole melts. While conventional methods for synthesizing titanium borides require temperatures above 1000 Celsius or specialized thermal approaches, this work employs as ionic melts as a significantly lower temperature of 120 degrees Celsius. This study focuses on the electrochemical behavior of imidazole and the possibility of co-deposition of titanium and boron. We provide mathematical analysis and thermodynamical calculation and conduct an electrolysis at 120 degrees of Celsius, and we obtain thick deposition at nickel and stainless steel cathode at current densities of 20 to 40 milliampere per centimeter. To increase the crystallinity, the samples were annealed at 600 in argon atmosphere. Overall, thermodynamic calculation, temperature, and electrolysis experiments confirmed the possibility of electrochemical synthesis of titanium borate refractory compounds. And XRD analysis after at 600 degree Celsius in argon indicates the formation of titanium borates with approximation ratio 1:1. Thank you for your attention.
Thank you. Any question, please?
I would like to ask a question.
Microphone, please.
The title is Electrochemical Synthesis of Titanium, is it titanium? Tantal.
Yes, titan.
Okay. Titanium and boron.
No, it's titanium borate.
So
we obtained titanium borate compound.
Okay, so the minus there is just it's a titanium boride.
Yes.
Thank you. And there is no variation in stoichiometry. It's well formed and
all peaks on XRD compared to titanium borates.
And the nickel reflects are substrate.
Yes, substrate.
Thank you.
What is a X-ray diagram? Nickel. It is a nickel. Yes.
It's we use nickel and stainless electrodes, and it's the formation six compounds on its electrodes.
Yes.
The titanium boride deposits on the nickel.
Nickel and stainless.
Thank you. Good luck in your study.
Thank you very much.
Well, next poster.
Good afternoon, dear participants. My poster is about the influence of crystallization rate on the structure and characteristics of martensitic transformation in alloys of the cuprum aluminium magnesium system. Our motivation is to research cuprum aluminium properties. This alloy are promising functional material with a shape memory effect due to their low cost, good manufacturing, and ability to undergo thermoelastic martensitic transformation. Their materials can be applied in sensors, actuators, micromechanical systems, and cryogenic device. It is known that the functional properties of cuprum aluminium magnesium alloys stronger depend on crystallization conditions, which affected the phase composition, grain size, and martensitic morphology. The objective of this study, which was to investigate the effect of cooling rate on the structure and mechanical properties of cuprum aluminium magnesium. In our experiments, this alloy was produced by vacuum induction pressure casting using the Indutherm MC16 system in the argon atmosphere to prevent oxidation of alloy elements. The casting were formed under different cooling temperature, medium, low, allowing variations of the crystallization rate. Phase composition was studied by X-ray diffraction analysis using drone 3M diffractometer, and microstructure was and elemental distribution were investigated by scanning electronic microscopy and ADX spectroscopy. Mechanical properties were investigated by Oliver Parr method. The results showing that the cooling rate significantly affects the structural formation of the alloy. The influence of crystallization rate on the structure and properties of cuprum aluminium magnesium alloys was investigated, and it was shown that cooling conditions significantly affect the phase composition, microstructure, morphologically, and microhardness of the material. Rapid cooling promotes the formation of the fine disparate microstructure and increases hardness, which is promising for development and functional shape memories elements.
Thank you. Any question, please?
Thank you for the report. You mentioned low and medium cooling rates, yeah, and this is casting.
Yeah.
So how did you achieve the difference in cooling rates?
We use atmosphere where the cooling was in room temperature, low temperature near zero, and minus 100 by nitrogen.
So you just pour your melt into the.
Yeah, we cool the form where we pull our liquid metal, and we cool this previously but to minus 100 degrees, and then after that pull their our casting. It was under the pressure in the vacuum.
Quenching.
Is it quenching, or because you are speaking about different cooling rates? Yes. So
Cooling rate.
if you just pour your melt into something cold, you are not controlling cooling rates. They are, yes, they correlate with the temperature of the environment you pour it into, but you hardly control anything.
Yes, but we more investigate. Okay, it's probably my more mistake by telling by this form. It's more likely we watch how changes our structure by cooling in this temperature to this temperature and this temperature. So
So the main question is
temperature.
Quenching or just putting it inside a cold.
You put it inside, yeah.
Okay, thank you.
Thank you. Yes, please.
One small question. Did you try to calculate the cooling rate? I mean, in Celsius per minute or Celsius per seconds for your volume of
Yes,
material?
but right now I can't tell you the result of our calculations because, sorry, I don't remember right now them.
Okay, because it will make the results comparable with other literature. Okay, thank you.
Thank you one more time. Yes,
thank you.
Please, next presentation.
Dear colleagues, I want to introduce you our work about the mechanical properties of high entropy alloys based on the tungsten, iron, cobalt, nickel, graphite alloys. So the high entropy materials in the last decade is one of the promising materials for different applications for high temperature, for the tooling, for the construction materials. But some tricky point in that materials is the combination of different properties in the one materials. For the one case, the most frequency used strengthening mechanism in the high entropy alloys is the solid solution forming. Compared to the different entropy of mixing and the initial chemical composition, different solid solution could be formed with the single solid solution or some dual phase structure. Another point is that in the industry, the most important things to increase the strength is the reinforcing for the particles or for the fibers. In our work, we try to investigate the additional carbon for the high reactivity system, especially based on the tungsten, to prepare different quantity of the tungsten carbide in situ during the sintering. So first of all, we prepare the high entropy materials by mechanical alloying during near 15 or 20 hours in the planetary ball mill in the petrol liquid, so to prevent the cold welding and increase the homogeneity of the mixing. After that, we consolidate the powder mix by the spark plasma sintering. So, and add in the initial charge different quantity of the carbon. So after sintering of the pure high entropy alloys, we have this BCC solid solutions near 900 megapascal of compressive strength. So during the increasing of the quantity of the carbon, the strength of the compressing also increased to the 1000, 1100, but the maximum concentration promote to degrees of the strength because the porosity of the system also increased. During the in situ forming of the tungsten carbide is the relatively high exothermic reaction in the system. So on the low concentration, the SPS pressure can improve it, but from the a big amount of the carbon, the porosity effect has the significant role in the strengthening of the our materials. So thank you for your attention.
Thank you. Any question, please?
I have a few, perhaps, if I may. The first one is where did nickel go from the title of the presentation?
It's interesting. I fixed it during the acceptation of the final thesis in the program and in the thesis. Everything is good, so it's my mistake.
It's just here. On the serious side, or less joking, yeah. This is a four element alloy.
Yeah.
Middle.
You call it high entropy.
Yeah, middle entropy.
It's a middle entropy.
It's a mid entropy, and again, it depends on the definition. I wanted to ask whether you just call it from the number of components.
No.
Or do you apply some some qualitative measure of the entropy induced in the system?
No, we don't measure.
So it's just
we only calculate and measure the quantity of the component.
And one last is the mechanism. Did you perhaps look into why carbon strengthens the material so much?
We can compare it with the fiber.
No. I mean, you definitely without carbon additions, you had around 500 MPa, and with carbon you reached up to 1100. So clearly, carbon improves strength.
Yeah, by the formation of the tungsten carbide.
So the alloy is not high entropy alloy anymore after introduction.
It's BCC matrix metal composite.
Okay, so there is a tungsten carbide and other three components. They still are in solid solution between us. Thank you.
SPS setup. It is a commercial one or laboratory made?
It's in our lab in the our university. It's quite a big machine. So it's like, you mean the technology is a commercial or
yes?
Yeah. For today it's a commercial. But name but fast or so different names for the technology. But
no. I mean the setup you used for.
Yeah, it's a big commercial machine.
Big commercial. And what value of pressure do you use?
15 megapascal.
15?
Yeah.
It is very small.
Oh, kilonewton. Sorry, it's 25 or
100
megapascal.
40 as a rule. 100 megapascal. In SPS. 100, 200 maximum.
No, that's
something is wrong there. 30 to 50, 50 is a low.
50 is a lot, up to 100. We, as a rule, we used 90 megapascal.
technique. It's quite a big pressure. No, for our machine, the relatively
Commercial.
Small.
yeah,
This.
20.
That's up to 50.
Yeah, it's yeah, quite big for our because yeah.
And if I perhaps may one more. Sorry. About the porosity, could you clarify a little bit? Because I thought Vlad would ask that, but he's silent.
What has happened? Yeah.
So you say that increasing porosity
Yeah.
also improves the strength. Is it correct?
No. It's decrease the strength.
Okay, so it was just what I heard.
I mean, the increase of the quantity of the carbon could decrease after 10% the strength due to the forming of the porosity.
So what is the atmosphere in that SPS setup?
Vacuum.
And porosity comes from?
It's a high exothermical reaction. If we increase the reactant like the carbon, the integral exothermic reaction also increases. So the energy is quite big.
Okay, still, what happens? How do pores form in that case? You have no combustion products.
No, we don't investigate it. We understand our critical point of the carbon content and stop on it.
So perhaps the reason is not directly carbon, because what can go wrong with it? You cannot form CO or CO2. Your
maybe we should to deeply investigate. Maybe it's not the porosity; it's a residual carbon.
That's more probably, yeah, I think.
Because the tungsten quantity for the reaction also decrease during the increase the carbon.
Yeah, there are other elements that can form carbides, of course.
Yeah.
In your system, but
yeah,
this perhaps.
Clear.
Thank you.
Yeah.
Next presentation.
You have EDX or elementary analysis of your alloys?
Yeah.
This analysis in post or not?
Yeah, sure. So
Because this atom percent not 15, it's because your alloys not clear, and this percent changes.
You means should to show the evolution of the carbon content on the EDX?
Yes.
But yeah, for the ADX methods, the low energy of the adsorption on the detectors. Carbon, boron, nitrogen, oxygen has the energy near 0.2713. So the big portion of energy adsorbed on the detector. If we would have the detectors like energy losses for the TM, we can investigate the carbon content. Because atomic percent control for the ADS, it's impossible. For us, the main thing is the phase composition when we can see the tungsten carbide. It's our subject of this work. So yeah, but thank you for your feedback. We included for the maybe articles or something like. Thank you.
Thank you. Thank you. Please. I'm sorry. We should hear.
Thank you. Today, refractory metals and especially molybdenum could be used as high temperature materials, but it needs to be alloying with titanium, tantalum, and chromium elements. If we will produce this mix by the mechanical mixture, it could be a reaction between tantalum and chromium or chromium and titanium. So this reaction could be a cause for formation intermetallics, and as it calls in the literature, it's Lewis phase. It's but depend on mechanical properties and oxidation resistance. So in this work, in this study, we investigate how to make a mixed between these elements with a high homogeneity. And it was obtained a two type of mixture. In the first case, we use molybdenum as a metal powder, and it was shown that diffusion becomes to grain boundaries, and it isn't homogeneous. But if we use all as oxides, we can have very ultra-fine powders with homogeneity.
Distribution.
Thank you. Distribution of all elements. And in this case, there is no place where will be contact titanium and chromium or tantalum and chromium, because all of this is in the molybdenum matrix, and because of much more continuum of molybdenum. So this method could be used for preparing powders, which in the future could be formed by SPS, for example, or other methods.
Thank you. Yes.
Yes. Question.
May
May I?
Yes, yes, of course.
So the primary motivation, you said you don't want pure metals in contact. Then you take oxides,
yes,
mix the oxides,
yes,
and that's the product. That's what you sinter in SPS.
No, we mixed oxides.
Okay.
Then we do calciothermic reduction. So we add calcium hydride, heating this mixture, and as a product we have mix alloys of metals and calcium oxide. Calcium oxide could be dilute with water,
yeah,
and other acid. We used acetic acid. Yes, and here is
so you basically produce calcium acetate, which is soluble, and you just rinse it from the powder, and you have fine mixture of. Okay, okay, nice.
And as we can see from this microstructure, the size of powders is about 1 micrometer.
Another question is your. You said it with a. You were sure that no contact between tantalum and chromium happens in that finely distributed powder because of the higher fraction of molybdenum, significantly higher fraction of molybdenum.
It's not only molybdenum reflection. If we look at the XRD pattern, we can see that here is reflection from tantalum and molybdenum, but when we use molybdenum as a metal, so that's there is. But if we use molybdenum as oxide, we can say that part of tantalum
Dissolves.
Dissolves, yes, in the molybdenum. So we saw that our peaks of intensity has not strain.
Okay, just to clarify, so when you use several oxides, molybdenum oxide and what is it? Tantalum, you have solubility from one oxide to the other.
Oxide is not solubility. Solubility is between metals after reduced.
After reduction.
Yes, it's this. When we reduced oxides, metals is ultra fine, and they can, by the contact between two particles of metals, it could solid solution made.
That's interesting because you still have your calcium oxide in there, which is insulating for diffusion between the grains, let's say, of what used to be oxide of one metal or the other. Because you reduce with calcium, yes?
Yes.
So calcium has to come to the surface of the oxide grain.
Yes.
Interact with the oxygen inside that grain.
Yes.
And where does it go? It stays where it was.
It stays, but as an oxide, not as a metal.
Yeah, but how the diffusion of, for example, tantalum to molybdenum happens at this stage when you have calcium oxide around your initial oxide particle. That's interesting because if it happens, actually, it probably has to involve calcium oxide. Maybe not, but that's interesting.
Actually, some part of our mix, it's like conglomerate. And inside this conglomerate is oxide of calcium. So after heating, we need post-reduction milling. When we post-reduction milling, it's mechanical influence on our mixture. So it could also increase reaction, not reaction, but maybe
That area between the actual
and also it helps us to separate the oxide of calcium. And after this, as calcium oxide is so very active, react with water, it could be easy separated from mixed.
Yeah, but you have insoluble hydroxide after that. You still have to wash it with your what was there? Acetic acid.
Yes, calcium hydroxide is react with acetic acid, but acetic acid is so типу слабка кислота, вона
weak, yeah. Weak acid.
And it's not react with metals. And the purity of these powders is
How comes it reacts with calcium?
Huh?
It reacts with calcium. Calcium is metal.
No.
I'm sorry, just joking. I understand that you are speaking about the interesting metals, not the calcium one.
Yes,
Thank
sir.
you.
Any question, please?
Thank you very much.
It's enough, I think. Thank you very much for a very interesting presentation. Well, our plenary session is finished. And now is lunch, time for lunch, and we will meet at 12 o'clock.
1 p.m.
1 p.m. Ні, 2 p.m. At 2 p.m. Thank you.
Повинно працювати, але... Так, працювало. Дивіться, по сходам з нашого... Там, де відкривалась конференція. Там, де літачок ото. Напроти літачка ліворуч? After the lunch, we will have our next oral session, refractory metals, refractory metals and alloys. The session will begin with Alexandra Tolochina keynote speech.
Dear colleagues, we continue our work, and the first presentation after lunch will be done by keynote speaker Alexandra Tolochina. Солнце. I don't know. Yes, да. Are you here, us?
Yes, I'm here. I'm ready.
Yes, of course.
Can you see
well,
my
please,
presentation?
you can start your presentation. We are hearing you.
Good afternoon, estimated colleagues. It's a privilege to present our latest research here at the SAMSONOV 2026 conference. And today I will discuss advanced approaches to the microstructural design of powder-derived high-temperature materials. Specifically, we will focus on their evolution under deformation processing. Energy efficiency directly determines the performance of modern industrial systems. Today, global energy consumption is rising rapidly, driven by high-tech industries, large-scale data centers, and global digitalization. To meet these growing demands, we cannot simply increase power generation. Instead, we must fundamentally improve the efficiency of power and processing machinery. This critical challenge requires a new generation of energy systems, and ones that demand unprecedented efficiency, reliability, and cost effectiveness. And this is exactly where advanced material science becomes the key factor. Currently, the development of next generation energy system, such as modular reactors, hydrogen gas turbines, and ultra supercritical steam systems demands a drastic increase in operating temperatures. In the working zone, temperature now reach up to 1100 degrees Celsius. Naturally, this places demands on the structure materials and their manufacturing technologies. When operating under severe mechanical and thermal stress, these components must exhibit exceptional high temperature strength, creep resistance, and long-term reliability. And to meet these critical requirements, specialized heat-resistant and oxidation-resistant alloys are developed and utilized. The most widely applied classes include traditional nickel-based nickel-based superalloys, cobalt or iron-based superalloys, intermetallics, new higher entropy alloys, and however, their ability to withstand these extreme conditions is determined not only by their chemical compositions, but by their microstructural design. And this brings us directly to the core of our study. As we know, microstructure dictates material behavior. It determines which strengthening mechanism can be activated at elevated temperatures. These include classic grain boundary, solid solution, and dispersion strengthening, both dispersoid and precipitation types. To activate this mechanism most effectively, we leverage the distinct advantages of powder metallurgy technologies. Traditionally, casting has been the primary route for producing heat-resistant alloys. However, standard casting has reached its development limits. In contrast, powder metallurgy offers significantly broader opportunities. It allows us to design completely different microstructural architectures that are simply impossible to achieve by conventional melting. The key benefits here are well known. The ability to form gradient or matrix structure, skeletal materials, and stable nanostructure states. However, this technology has two critical limitations: residual porosity and prior powder boundaries, and its major structural defects, severely degrading the final properties of the material. And eliminating these defects is the main focus of our work. So, to eliminate these defects, we apply deformation-based processing. While plastic deformation ensures basic consolidation, it is the intensive, severe shear component. They play the key role. This shear component effectively heals planar porosity and significantly improves structural homogeneity. We evaluated this approach using two representative systems. First, it's iron aluminum intermetallics, and second, nickel-based heat-resistant alloys. The general technological road of powder metallurgy may be represented. It's a follow. It's important to know that deformation-based methods are involved at several stages of the overall processing chain. In one case, deformation can be used for the comminution of the initial powders and for phase synthesis for elemental powder mixture. In another case, deformation can be applied to both to powder consolidation and to shaping of the workpiece. To produce powder-based components with a microstructure containing a minimal number of volumetric and planar defects, we develop several deformation schemes for powder processing. This technology referred to as direct powder forging and may be considered an alternative to additive manufacturing. And simulation of the powder deformation process made it possible to determine the stress-strain state, the axial and radial strain components, and the porosity of the specimen. Based on these simulation results, the most suitable temperatures and deformation schemes ensuring powder consolidation and The closure of volumetric and planar porosity were selected. Experimental investigation was then carried out using these optimized processing routes. Let us look at the structural analysis of iron aluminide after direct powder forging and comparison with the casting materials. So, as you can see, the microstructure is ultra fine with an average grain size of just 20 micrometers. Crucially, the presence of prior powder boundaries and porosity is negligible. And this is massive improvement compared to conventional cast materials where grain size reach several hundred micrometers. This fine-grained structure directly dictates the superior high-temperature properties. Our powder processed material operates reliably at 600 to 650 degrees Celsius, maintaining a high yield strength of 350 to 500 megapascals. In contrast, the cast counterpart fails much earlier. Its limit is 550 degrees with a lower yield strength. Thus, our approach guarantees effective grain boundary strengthening, providing superior performance in both strength and thermal stability. Moving forward, future microstructural refinement could push these properties even higher. And to achieve effective microstructural refinement, we utilized high-energy planetary ball milling. This process acts as a method of severe plastic deformation. During mechanical milling, we achieved two critical goals simultaneously. First, the direct solid-state synthesis in intermetallic phases from elemental iron and aluminum powders. And second, the transition of the material into a nanostructured state. Importantly, the huge density of deformation-induced defects generated during milling time significantly accelerated diffusion and driving rapid phase formation during subsequent heating. We tracked the structural evolution using X-ray diffraction as presented on these plots. If we look at the profile of iron line, the initial sharp doublet completely disappear after 4 hours of grinding. Instead, we observe a dramatic broadening of the peak, which indicates severe work hardening and structural refinement. To separate the contribution of crystallite size and lattice microstrain to this broadening, we applied the Williamson-Hall graphical method. Our calculations summarized in the table confirm a profound structural transitions. The coherent scattering domain drops sharply from 85 nanometers down to just 32 nanometers. Concurrently, the dislocation density increases by 2 orders of magnitude, reaching value of 4.16. These outstanding values are highly representative of materials subjected to severe plastic deformation and lay the foundation for the exceptional properties of our final components. Moving forward, we discovered that pre-milling decreases the exometric reaction temperature for iron aluminide synthesis by approximately 50 degrees Celsius, and allowing the process to proceed predominantly in the solid phase, in the solid state. By combining direct powder forging with mechanical milling, we achieve complete control over the final morphology. As you can see on the slide, we can tailor the material into either an isotropic or highly anisotropic structure. The anisotropic architecture provides a significantly higher degree of structural refinement. Consequently, they yield superior mechanical performance, specifically enhance bending strength and fracture toughness at room temperature. To understand the physical origin of this enhanced fracture toughness, we analyzed the crack propagation kinetics. Please look at the loading curve and the corresponding micrographs. At position 1, microcracks initiate at the notch, but upon loading, they interact with the ultrafine grain boundaries. At position 2, we reach the peak load where secondary crack forms. Importantly, this secondary crack branch out perpendicular to the primary one, effectively shielding the applied stress. At the position 3 and 4, due to the low shear stress at the crack tip and clean grain boundaries, the crack is forced to reorient and delaminate within the grains. As evidenced by the fracture surface on the right, the crack path divided by 200 to 300 micrometers. This massive deviation absorbs a huge amount of energy and making our anisotropic material exceptionally damage tolerant compared to the unground brittle counterpart. Finally, to evaluate the structural integrity and map the true orientation effects of our forged materials, we tested fracture toughness in 2 distinct crack propagation planes. As illustrated in the diagram on the top, we machined small size notched specimen relative to the forging axis. In plane 1, where the crack propagates across the elongated grains, we achieved an exceptional fracture toughness, nearly 30 megapascals. And in plane 2, where the crack plane coincides with dynamic delamination direction, the fracture toughness is roughly 20% lower and yielding 23 megapascals per meter. To execute this mechanical test on such compact specimens accurately, we developed and employed a custom 3-point bending fixture with special extension grips. Importantly, this slight 20% decrease is solely attributed to grain anisotropy. The fact that the material retains such high toughness even in its weaker orientation prove the complete absence of harmful impurity segregations or residual defects along the boundaries. Now, let us examine the high temperature mechanical behavior at 700 degrees Celsius, where we observe a distinct stress differential effect. As you can see from the central curves, the yield strength in compression is nearly double that in tension. This phenomenon is driven by the growth of deformation-induced micropores under tensile loading, which promotes accelerated softening. To uncover the precise deformation mechanism, we performed a detailed transmission electron microscopy analysis shown in this figure. At 700 degrees C, our materials operates in a regime where dislocation slip transitions into diffusion controlled creep. Diagram clearly illustrate the interaction between dislocation and precipitation particles. When particles are smaller than 0.5 micrometers, they act as highly effective barriers. As highlighted in diagram in the bottom, the dislocation bypasses small particles through climb processes, which allows the materials to maintain its structural stability. The real triumph of our technological road is presented in the creep curves. The anisotropic structure exhibits a steady state creep rate that is roughly half that of the isotropic composition, isotropic state. Even more impressive, it is 4 times lower compared to conventionally sintered samples of identical composition. Therefore, the synergistic combination of preliminary powder milling and subsequent closed die forging successfully delivers high performance components with outstanding high temperature strength and exceptional creep resistance. To achieve maximum structural refinement and unlock dynamic recrystallization, we developed a novel multi-stage deformation scheme. Is illustrated on the left. This road utilized a specialized multi-pass processing assembly, where the powder perform undergoes sequential compression steps within protective steel containers. The right-hand plot demonstrates the real-time compaction mechanics during forging at 1200 degrees Celsius. Here we can see clearly track the evolution of forging force across the first, second, and third deformation passes. By analyzing these structural and kinematic parameters, we determined the fundamental kinetic laws governing the processes. The calculated Zener-Holomon parameters here reach a value of 2.72 10 to the 14 under strain rates ranging here. And the critical strain required to trigger dynamic recrystallization was found to sit tightly within the 15 to 30% range. According to our physical models, increasing the strain rate and temperature naturally expands the crystallization window. Consequently, for our specific intermetallic system, the optimal temperature window to guarantee full dynamic recrystallization and is established between 1150 to 1200 degrees Celsius. This precise window ensures the production of completely homogeneous and defect-free nanostructure components. After modeling the multiple deformation process, we identified the optimal processing conditions, including both the temperature range and deformation parameters. This calculated regime were then used for experimental validation. The simulation results made it possible to better understand the evolution of the material structure during deformation and to select conditions that provide the most efficient consolidation and structure refinement. Multi-stage hot deformation leads to the formation of large number of fine particles distributed along the grain boundaries. Most of these particles are smaller than 0.3 micrometers, which is very important both for effective precipitation strengthening and for suppressing pore formation at the particle matrix interfaces. Transmission electron microscopy revealed that the microstructure after deformation contains a large number of fine, nearly isotropic grain with sizes in the range 0.5 to 1 micrometers. In other words, dynamic recrystallization not only help us to remove impurities and defect associated with prior powder boundaries, but also promotes the formation of a new ultra-fine grain structure. As a result, the material produced by multiple forging demonstrate a significant increase in low temperature strength. This improvement is mainly associated with the grain refinement and with the dispersion of oxide particles throughout the structure. Another important features it's the absence of slit-like pores, which normally act as stress concentration and cracked initiation sites during brittle fractures. The fine-grained, highly defected structure formed after repeated deformation allows the yield strength of the material to remain significantly higher, up to temperatures is about 500 degrees C. However, the higher temperatures, at the higher temperatures, the strengthening effect becomes less pronounced. This indicates that the grain boundary strengthening gradually loses its efficiency at elevated temperature. At temperatures approximately 500 degrees C, grain boundaries no longer act as the main obstacles to plastic deformation because diffusion along grain boundaries becomes much more active through the cobble creep mechanism. In addition, lattice resistance decreases due to cross-slip processes and vacancy associated mass transport. Under these conditions, the dominant contribution to high temperature strengthening comes from incoherent dispersed particles, and which remained effective up to temperatures approaching 0.7 of the melting temperature. And therefore, for future improvement of high temperature performance, other strengthening mechanism must be introduced, especially solid solution strengthening and dispersion strengthening. Now, let us move from the pure iron aluminide to the alloyed system. Specifically, these slides illustrates the experimental data obtained with molybdenum additions. It leads to noticeable increase in both yield strength and ultimate tensile strength, while ductility gradually decrease with increasing molybdenum content. The higher temperature tensile curves shown in the figure compare materials produced from mechanical mill powders consolidated using single stage and multi-stage deformation rolls. Their results demonstrate that reducing the molybdenum content decreases and the ultimate strength, whereas the plasticity increases. The loading curves show that maximum strength is reached rather quickly, followed by gradual softening during deformation. This softening becomes more pronounced in alloys with higher molybdenum content, which is typically for materials where diffusion controlled creep mechanism become dominant. At comparable alloying levels, the samples produced by triple forging exhibit significantly higher yield strengths than those processed by conventional forging. This behavior can be explained by the combined strengthening effect resulting from the grain refinement, particle dispersion, and diffusion process due to molybdenum alloying. And even great advantage of this combined strengthening mechanism is expected under the creep conditions. Molybdenum significantly improve creep resistance of iron aluminides. For the alloyed material, the calculated creep activation energy approximately 170 kilojoule per mole in this temperature range. Is characteristic of a predominantly dislocation controlled creep mechanism. And for alloys containing 2 or 5 weight percent molybdenum, the activation energy increases to approximately 360 and 220 kilojoules per mole, respectively, and indicating a larger contribution of diffusion-related processes at these elevated temperatures. The experimentally obtained stress exponent values are characteristic of dislocation diffusion creep mechanism. In this case, molybdenum dissolved in the matrix reduced diffusion rates, while second phase particles effectively hinder dislocation motion and result in improved high temperature strength and creep resistance. To achieve future performance gains, we shifted our attention to complex alloy with borides, aiming to form secondary phases. The slide presents the result of this boride reinforced iron aluminides. When we tested this material at high temperature, we found that the standard grain boundaries stop acting as effective barriers to deformation because atoms begin to diffuse too quickly. Instead, the heavy lifting is taken over by these stable boride particles, which successfully block material deformation. As a result, our chromium diboride reinforced alloy demonstrate excellent resistance to creep at 800 degrees C, and even more impressively, as the alloy reinforced with lanthanum diboride maintained an incredibly low deformation rate, even when pushed to 850 degrees C. Having discussed iron aluminides, I would like now to shift our focus to the second part of the study, which deals with nickel-based superalloys. These materials are difficult to deform, traditionally requiring a very slow, expensive, and time-consuming processes called isothermal forging to achieve superelastic behavior. While it works well for massive components like large power turbines, this slow road becomes economically efficient when we scale down to mini and micro turbine systems. And to solve this, we developed a promising alternative, the DPF technology processing route. The first step, subsolvus, single-stage deformation at lower temperatures give us a highly dense structure. It does leave behind minor structural defects like planar porosity and prior powder particles boundary. But it successfully preserves a high volume of the key strengthening phases. The second step, supersolvus, here heating the materials above 1200 degrees C acts as a healing stage. It eliminates the porosity, recrystallizes the problematic boundaries, and triggers the growth of finally dispersed strengthening precipitates. The ultimate proof of this efficiency is on the right. Our stress strain clearly show that after this heat treatment, the superalloys exhibit much higher yield strength and an excellent work hardening rate. By increasing the volume fraction of this gamma precipitates, dispersion strengthening becomes the dominant mechanism and providing exceptional high temperature performance of these powder superalloys. To achieve the absolute maximum strength, creep resistance, and fatigue life for these superalloys, we need to find the perfect balance between different populations of the strengthening gamma prime phase. Standard heat treatment allows us to partially transform the large coarse gamma phase into fine, highly effective secondary precipitates. However, a major challenge remains. Even after standard treatment, a certain amount of this primary phase gets trapped along the old powder particle boundaries and preventing full recrystallization and leaving weak spots. This is where our triple forging approach proves its value. As you can see from the processing schematic and microstructure, repeating of deformation cycle successfully breaks down and crystallized those problematic boundary region. It forces the trapped gamma prime phase to redistribute completely and precipitate in the form of uniform ultrafine strengthening particles throughout the entire matrix. The ultimate payoff of the structural homogeneity, it's clearly demonstrated in the bar chart, comparing one-step forging to triple forging. And we see a substantial increase in yield stress across all tested high temperatures, especially when combined with a higher deformation temperature. We have successfully engineered and highly homogeneous maximum strength microstructure. So, in conclusion, we have shown that the combining of powder metallurgy and deformation processing provides an effective way to control the microstructure and strengthening mechanism of heat resistance alloys. And in the future, our work will focus on optimizing combined strengthening mechanism, developing more cost-effective processing roads, and maybe adapting these technologies for advanced turbine applications, including mini and micro turbine systems. And thank you for your attention. And we gratefully acknowledge the financial support provided by the National Research Foundation of Ukraine, which made this study possible. Thank you so much.
Thank you, Dr. Toluchina, for a very interesting presentation. And before we started the discussion, I'd like to ask one small question about chemical composition. It will be done in weight percent, yes? Ferrum aluminium.
Yes, we used weight percent.
In atomic percent, it is equiatomic state. In atomic
it was
percent.
50-50. No. For iron aluminides, we used atomic percent iron 28 aluminium atomic. It's equal to approximately 16 weight in percent.
Yes.
Aluminium.
28 atomic percent ferrum aluminium. Yes. In atomic
yes.
percent.
Yes, atomic percent.
And one more question, small. What's the useful from powder metallurgy of this composition in comparison with traditional metallurgy? Maybe enhance it plasticity, etc.
Of course, powder metallurgy give us more advantages to obtain structural refinement. For example, it's the first state that I discussed in my presentation. Then with this, and we can obtain new morphological states, new composition, new microstructural states, which allow us obtain more higher ductility in these materials.
Thank you. More question, please. Please.
Thank you for your presentation. In slide number 25, I saw you use the lanthanum hexaboride as an additional phase for in one of your alloys. And what was the main purpose to use this compound?
We use this compound to increase yield strength at elevated temperatures, first of all. And we obtained evidence that this composition has promising influence of our pure iron aluminides.
And the result is?
Yeah, it's enhanced at, for example, at elevated temperature at 750 degrees Celsius, we have good results of yield strength comparison with other editions.
Okay, okay, thank you.
One more question.
Yes, please.
Well, I have one more small question. Slide 15, please. Yes, phase composition. You used for production of this alloy ball milling, yes, da? Elemental powder, ferrum and aluminium. 1 hour of milling. It is practically pure aluminium X-ray diffraction.
No,
Where ferrum? Where line of ferrum?
With the ferrum, it's this peak, this big peak.
Ferrum, elemental ferrum was in a BCC state.
Yes, of course. It was BCC state. We developed this ball milling with during the 10 hours, and on the after first hour in the composition we can observe iron and aluminum. It's only we can obtain iron aluminum after approximately 4 to 10 hours.
Thank you. Thank you very much for the interesting results presented at our conference. Good luck in your future investigation. Well, continue our work. The next presentation. Will be done by Tatiana Solntseva from Frantsevich Institute for Program of Material Science. Please.
Kinetics of recrystallization during the synthesis of nickel intermetallic compounds. And the loss, as you can see. Aluminum is the main alloying component of heat-resistant alloys, which after hardening and aging of the alloys releases intermetallic compounds in a dispersed state and increases the heat resistance of the material. When producing yttrium oxide reinforced nichrome by reaction sintering and semi-mechanical processing, the formation of unidirectional intermetallic inclusions was discovered, which made it possible to significantly increase fatigue strength. The effect of fibrous structure formation is possibly caused by thermal processes during recrystallization and aging of powder alloy. Understanding the nature and establishing the mechanism of formation of such a structure is necessary for targeting control of the processes of formation of a given form of intermetallic precipitates of high heat-resistant nickel-based alloys. The semikinetics of the processes occurring in the pressed sample during heating from the heating temperature to the synthesis of intermetallic compound is directly presented. Non-linear thermal behavior with characteristic temperature spikes is observed. Initial stage of relaxing, running thermal waves, and Andronov-Hopf bifurcation phase transition are clearly observed. The active phase of aluminum recrystallization, non-linear semikinetic processes are visible before the onset or beginning of recrystallization. During the composition of oxide, the endothermic effect and the auto-wave energy dissipation are observed. A longer period of nickel recrystallization process is observed. This is accompanied by a charge in semikinetic trajectories. We can see several stages of recrystallization processes, stages of nickel recrystallizations. In a short period of time before the beginning of synthesis, a change in several semikinetic trajectories is observed. We can observe several trajectories of the process. The reaction region of the synthesis of an intermetallic compound of equiatomic composition. The temperature increase trajectory has a smooth monotonous character, indicating complete synthesis of the compound. Synthesis when the we can see the rise of the curves. Microstructure of dispersion hardened alloy after compression from 50 to 75% and aging 1000 magnification. The upper left corner shows a sample blank cold rolled with a reduction ratio of 95%. The initial sample small and the long sample after deformation. The lower left corner shows its structure after aging. On the right is the structure of alloys subjected to different reduction ratios. The fatigue strength and cycling heat resistance of the alloy. The developed dispersion strengthened alloys with directly oriented intermetallic inclusions have high fatigue strengths with equally high heat cyclic resistance. To the right part of the figure. Fatigue strength and cycle heat resistance of the alloy of nichrome. A model of the heat protective honeycomb panel of a reusable spacecraft. Due to the high ductility and fatigue strength of the obtained alloys, a model of honeycomb structure was manufactured using thermosetting brazing. We can see one part and the honeycomb part of the panel and in the left and the whole panel after thermosetting brazing. And so that is the structure made from the nichrome after synthesis and thermomechanical treatment. That's all. Thank you.
Thank you very much. Any question? Colleague, please. One more very small question. Can you measure the thermal effects at the process of recrystallization? What type of setup do you use?
Сейчас посмотрим. We can see.
Yes, please.
More.
Please, this. How do you measure self-oscillatory mode of decomposition?
We didn't measure. We also saw the endothermic. Oh, сейчас 555. Endothermic effect we can see, and we didn't measure the quantity or qualitative or quantitative amount. We also see what processes take place in the sample. There are 3 thermocouples in the sample. This one, and this one, 3 thermocouples. 7 brown, red, and violet. And we can see all of them show the endothermic effect of decomposition of nickel oxides. And we didn't measure the calories or joules. So we also see the effect in the sample.
Thank you. Thank you. Any question, please? Thanks. And now will be coffee break. And after coffee break, you make
second report.
Yes, yes, yes.
Thank
We are
you.
waiting for you. Coffee break, colleagues.
Before the online poster session, I would like to give the floor to Tatiana Solntseva with the presentation of formation of dissipative structures in systems based on transition metals with dichalcogenides and refractory compounds. Please take the floor.
Dissipative structures in systems based on transition metals with dichalcogenides and refractory compounds. The study of evolutionary processes in non-equilibrium physicochemical systems and the mechanisms of the emergence of organized matter has become a central problem in modern natural science. Undoubtedly, understanding these processes will enable targeted solutions to a number of common problems in various fields of science and technology, and to a greater extent, the creation of new functional materials. To create new materials based on the principle of biological systems that maintain their non-equilibrium state due to the dynamic stability, due to the flow of negative entropy, in fact, due to the exchange of energy and matter with the external environment, it is necessary to establish nonlinear interaction mechanisms that are observed in compositions of transition metals with selenides. The discreteness of these compositions allows for the formation of dissipative structures in local areas and the stability of composition as a dissipative objects on a macroscopic scale. Until now, the stability of such systems has been associated with the occurrence of self-oscillatory reactions and the autowave processes they initiate. This raises the question of the nature of chemical affinity beyond the thermodynamic stability threshold of a non-equilibrium system. In this regard, the aim of the work was to clarify in more detail the nature of the formation of dissipative structures as a consequence of self-organization processes. To this end, interaction processes were studied in complex systems based on titanium with metals that have a greater chemical affinity for elements of the oxygen group than titanium, for example, aluminum. Decomposition, the kinetics, alpha degree of selenium yield of selenides in vacuum at different temperatures. Then we studied titanium selenium, zirconium selenide, and hafnium selenide. When decomposed in a vacuum, these selenides of metals of group of 4th, 5th group of periodic system and chromium do not completely release selenium. What? Вот. Это то или не то? Depends of degree. Сейчас много. Так. Да. When decomposed in vacuum, это уже было. Now, when introducing diselenides as components into metal matrix, either based on the metal that forms compound itself or into the alloy containing any of the named transition metals, weight losses are significantly reduced to the values of impurities that are lost during normal sintering. It should be noted that the decomposition of diselenides and sintering results in the formation of compounds with increased stoichiometry. This is due to the kinetic properties of the process and the catalytic properties of transition metals. This slide shows the stable thermodynamic state region of a number of transition metals, sulfides, and selenides from the 4th, 5th, and 6th A group of periodic systems. According to the thermodynamic data, all of these compounds arise beyond their equilibrium state, or as they say, beyond the threshold of the thermodynamic branch. Here we can see the region of formation of selenides and sulfides, of titanium, molybdenum, vanadium, etc., tantalum. The catalytic nature of the interaction between transition metals and selenium, Selen-2, is demonstrated by the experimental data on the composition of the gaseous medium using mass spectrometry during the heating of crushed sintered composites. It was found that the composition of this gaseous medium during sintering is dominated by atomic gas, selenium, while the sintered materials release a greater proportion of molecular gas, selenium-2. And this is that is тоже те саме. A study of the nature of distribution of elements in the vanadium-niobium selen-2 system showed the existence of selenium compounds of different stoichiometry beyond the threshold of their thermodynamic stability. There we can see concentration curves. Vanadium is the upper one, and niobium is the low one. Selen is the middle one. Curves. The boiling point of which selenium is 70 degrees centigrade. The irreversible decomposition reaction of transition metal selenide was modeled, involving the synthesis and recombination of selenium-2. Kinetic regularities demonstrated the existence of an oscillatory process as evidenced by the formation of a dissipative structure during selenide decomposition. A study of the composition of a titanium-based alloy with the molybdenum diselenide showed the existence of concentration waves clearly visible on the metallographic section of the sample during friction, which confirms the existence of an oscillatory reaction. A dissipative structure is formed during friction. Thus, outside the field of thermodynamic stability, the concept of chemical affinity proposed by Dedonde cannot be used. The phase composition of sintered VT14 alloy with 3% of molybdenum disulfide, molybdenum-2, showed the absence of aluminum sulfide, despite the fact that under equilibrium conditions, aluminum has a high affinity for elements of oxygen group, sulfur, selenium, tellurium, and the compound aluminium-2s3 should have formed, but we cannot see this substance in the figure. Diffraction. In the previous case, the phase composition of the sintered VT14 alloy with 3% molybdenum diselenide, molybdenum selen-2, showed the absence of aluminum selenide, despite the fact that under equilibrium conditions, aluminum has a higher affinity for elements of the oxygen group, and the compound aluminium-2 selen-3 should have formed, but we cannot see it. An analysis of the phase composition is presented. As with interaction with molybdenum sulfide, MoS2, the reaction with molybdenum diselenide, MoSelen2, results in the formation of similar phases, T2, titanium 2 selen, titanium selen 2, and aluminum titanium 3. Analysis of the phase composition is presented. Similar phases are formed with molybdenum sulfide, molybdenum and molybdenum diselenide, as with interaction with molybdenum diselenide MoSelen2. The distribution pattern of the elements indicates the absence of aluminum in compounds with selenium. That is, aluminum selenides are not formed within the thermodynamic range. Aluminum selenides should form under equilibrium conditions, equilibrium thermodynamics. It is once again confirmed that beyond the thermodynamic branch of the concept chemical affinity proposed by Dedonde for equilibrium systems and states cannot be used. Здесь то же самое. Так. The introduction of refractory compounds into self-organizing systems leads to the formation of dissipated structures with a wide range of synthesized refractory compounds. This follows from the analysis of the diffraction patterns of the composition with a 15 titanium, with a 14 with 15% titanium nitrate and 4% of boron nitrate and 4% boron carbide and 3% molybdenum sulfide, MoS2. The introduction into self-organizing system leads to the formation of dissipative structures with a wide range of synthesis refractory compounds. This follows from the analysis of the diffraction patterns of the composition with 15% of titanium nitrate and 4% of boron nitrate and boron carbide. Thermokinetics of a self-assembling titanium-based material exposed to an external heat flux on the sample surface. The system is observed to enter the energy dissipation regime. We also observe the system entering a steady state energy absorption regime. The introduction of refractory compounds into transition metal-based composition makes it possible to obtain dissipative structures with varying degrees of energy dissipation intensity. As a result, control the heat resistance of material. There we can see we heat the sample and the temperature of the sample also arises. But then we can see the steady state of the sample and we continue to heat the sample. But the temperature of the sample doesn't arise. By including refractory compounds formed by carbon, need to show it. That is the same, and this is the region left, the region of the center of the figure. Сейчас. Нет еще. Так. Там ще останній слайд залишився. Як мені зробити? Зараз скажу. Там, де boron, nitrogen and carbon. Останній слайд. Зараз я вам можу його показати, десь він повинен бути. Якщо. Oh, yes, this one. dissipative self-organizing inorganic system of different compositions under radiant heating. By introducing refractory compounds formed by carbon, nitrogen, boron, and other elements, it's possible to influence the dissipative properties of external energy dissipation, and these processes can be effectively used in the creation of materials for heat protective structures. That's all. Thank you.
SAMSONOV, thank you for the interesting presentation. Are there any questions?
I have no question.
Okay, thank you. And now we are beginning the online poster session of MSRC 2026, which brings together presentations from all conference sections. We are pleased to welcome all participants and presenters to this final scientific session of the conference. Let us begin. I see that Olena Lavrenenko is connected.
Yes, I'm here. Okay, yes. Could you show my slide?
Yeah, you can share it, please.
Oh, okay. I can share, but I think you help me to share the slide because I have no possibility to show it. My colleague told that they share the slide, maybe from Francevich Institute.
Just a moment, please.
Yes, thank you.
Okay, maybe it will be faster if you try to present your slide and we will help you with sharing.
I can't because I speak from by phone. I can't share the slide and it's very complicated for me. Now I'm in the way, but and can't show in the business is the trips. But I made it a small 5 minutes present speech without slide if it's possible.
We have found it. Just a moment, please.
Oh, okay.
Please
okay.
proceed.
Oh, okay. Could I start? Okay. Good evening, everyone, and thank you very much for opportunity to listen our presentation, show our slide. Also, the heterostructure based on rare earths and heavy metal oxides seems as perspective material for the creation new materials for green technologies, especially in the field of the evolution of hydrogen or degradation of the organic dyes and another save the environment. The aim of our work was the synthesis, formation of heterostructure based on rare earths oxides and heavy metal oxides, and test the activity in the degradation of malachite green solution under UV radiation. Synthesis of the nanopowders, binary nanopowders, was performed in the inorganic salts of cobaltum, cerium, lanthanum, and cuprum. and the precipitate was calcined at temperature 600 degrees within the 3 hours. And following formation of nanocomposites was with addition a very small amount of titanium dioxide, anatase modification formed by decomposition of methyltitanic acids. And the formation heterostructure was by the way of mechanosynthesis and following calcination of the powders. According to XRD data, in all cases, we obtained binary oxide system. For example, you may see the diffractograms where are present two phase of oxides. There is ceria oxides and cobaltum oxides. And about the heterogeneity of the composites, heterostructures confirms the same images when you can see the different particles, different size, different morphologies. In all cases, we obtain the oxide system, hence the lanthanum forms lanthanum 2 or 3 hexagonalic syngonal particles, and ceria form cubic fluorite type structure, and ceria cobalt 3 or 4 form cubical structure, and cuprum form more complicated oxides, include 6 molecules of cuprum O and 1 molecule of cuprum 2O. And the testing of photocatalytic activity was under UV radiation using 15 ampere xenon lamp and 300 watt of power. And malachite green solution was in concentration 10 milligram per cubical decimeter. The example control was performed by UV spectrometer. You may see the example of the spectra malachite green degradation for cobalt and ceria system. According to obtained data, we may confirm the presence of ceria. Ceria play important role in the photocatalytic activity of heterostructures, because independing on the nature of heavy metals, the level of degradation of malachite green is only 20% under UV radiation. Hence, but in the presence of lanthanum, the picture is different, because lanthanum with cuprum oxides is less active, because the degradation of malachite green is 27%, but in the presence of lanthanum cobalt system, the percent is 44%. Such difference could lie in the difference of the band gap energy of the general composite, all oxides, because for ceria it get 2.8 maybe electron volt, whereas for lanthanum oxides it is higher and get 4.3 electron volt. And according to our data, we think that the presence of ceria in the system, as I told before, ceria is general in the hetero composition, but lanthanum is not. The activity of lanthanum-containing composites determined by the heavy metals, because it is different. And a combination of such kind of elements could enhance the activity, photocatalytic activity of heterostructure on visible and UV region of activity. But our colleagues and we think that such kind of particles will be better used for not for photocatalytical but for electrocatalytical studies. And we try to do that with our Slovenian colleagues and our Ukrainian colleagues. Thank you very much again for your attention.
Thank you for an interesting presentation. Any
Thank
questions,
you.
maybe? I have a question. Tell me,
Okay.
please, if are there any abilities or instruments to change band gap energy within individual oxide compound? Maybe it can be temperature, maybe it can be or something else.
Crystallization, yes, but the best result we obtain when we add small amount the compound of different nature. For example, we have a lot results with use titanium dioxide and addition for ceria or nanoceria or argent or precious metal, noble metals show the difference in the band gap energy is result in activity at the destruction of the cationic and anionic dissolution. Hence, the better way is the small addition, another compound to move the band gap energy, conductive and valence zone for increase the activity.
Thank you very much.
Thank you.
And now I'd like to give the floor to Natya Barbakadze with the presentation Fast Transformations of Graphene Oxide Metal, Titanium, Zirconium, Molybdenum, Tungsten Composites in the temperature range of 100 to 1000 Celsius degree.
Okay,
Please
thank you very much. Thank you. Let me share my screen. Thank you. Is it okay?
We clearly seen.
So my work is about phase transformations of graphene oxide metal composites in the temperature range of 100 to 1000 degrees Celsius. This is joint work by the participation of three institutes. So why we paid so much attention to these composites? Because as it's well known, reduced graphene oxide metal oxide composites have a wide range of applications in the area of catalysis, optoelectronics, energy storage like lithium-ion batteries, solar cells, phototherapy, sensing, and wastewater treatment as well. So in this case, the role of reduced graphene oxide was to maintain the high electrical conductivity and to enhance the supercapacitor performance. We used the list of these compounds. Let me name them: the molybdic acid, tungstic acid, peroxomolybdic acid, peroxotungstic acid, ammonium heptamolybdate, tetrahydrate, ammonium metatungstate, tetrahydrate, ammonium paratungstate, hydrate, titanium tetroisopropoxide. So here you can see the main scheme or illustration where at the low temperatures the graphene oxide at 100 to 200 temperature, graphene oxide is reduced to is transferred to the reduced graphene oxide and leading to the formation of reduced oxide, graphene oxide and metal oxide composites. The metals in this case were titanium, zirconium, molybdenum, and titanium. As the temperature increased, increases, the oxides are transformed into oxygen-deficient oxides. The phase transformations of the obtained composites were investigated upon heating up to 1,000 degree Celsius, as I have mentioned at the initial stage of my speech. But the conditions in this case were different. It was in vacuum conditions, inert conditions, and reducing atmospheres as well. As you can see from the figure 1, here is presented the particle size distribution on the left side and the zeta potential measurements of the reduced graphene oxide molybdenum trioxide composite obtained from the graphene oxide molybdenum peroxomolybdic acid. At 300 degrees Celsius, as of the reduced graphene oxide tungsten composite obtaining from the peroxomolybdic acid composite at 300 degrees Celsius were determined that the corresponding curves that you can see demonstrate that the particle size of the composites were in range of 530 to 570 nanometers. Whereas the initial size of particles of the initial graphene oxide was 250 to 300 nanometers. So thermal treatment, as you can see from the zeta potential values has been decreased from minus 58 to 61 millivolts to the 24 millivolts. So it has its effect on the zeta potential as well. So depending on the XRD analysis, here we discuss showing these XRD patterns. Upon heating to 300 degree, the graphene oxide peroxomolybdic acid complex converts into an amorphous material. This is the green one. At 50 degrees Celsius, I forgot to tell this, was observed the graphene oxide, as it is marked here. So the obtaining or formation of the amorphous structure indicate the thermally induced transition from graphene oxide to reduced graphene oxide. So heating the graphene oxide peroxomolybdic acid complex in an inert atmosphere to 500 degrees Celsius results in the formation of reduced graphene oxide molybdenum sorry, my cursor is here. So formation of reduced graphene oxide molybdenum dioxide composite. In the temperature range of 50 to 500 degrees Celsius, the following phase transformations occur. So graphene oxide peroxomolybdic acid is transformed to the reduced graphene oxide molybdenum trioxide, and then reduced graphene oxide molybdenum dioxide is obtained. So the next figure is the pattern of graphene oxide peroxomolybdic acid complex, which was heated to the 1,000 degrees Celsius. It ends with the formation of molybdenum semicarbide. So let's move to the next figure. Figure 4. Here was heated the graphene oxide polyperoxide tungstic acid complex from 300 degrees Celsius to 500 degrees Celsius, which leads to the formation of the reduced graphene oxide tungsten O3 composite. So reduced graphene oxide tungsten trioxide is then gradually transformed into reduced graphene oxide and tungstic oxygen deficient oxide, let me say. It's a tungsten O2.9, and then it is transferred into the reduced graphene oxide tungsten dioxide, which at 900 to 1000 degrees Celsius leads to the formation of mixture, which consists of tungsten monocarbide and tungsten semicarbide. So figure 5 shows the transformation of graphene oxide, zirconium hydroxide. This is the blue one. To the reduced graphene oxide zirconium dioxide. It was at 500 degrees Celsius. It's red one, as you can see. And reduced graphene oxide zirconium dioxide at 1000 degrees Celsius. So as we can see from these results, zirconium has a little bit other behavior unlike the other metals. The graphene oxide zirconium compound complex does not undergo carburization and is instead results in the formation of a reduced graphene oxide zirconium dioxide tetragonal composite. It was very interesting for us because it was not characteristic to the other metals that were used from us. So the last one shows the gel samples, graphene oxide samples. So we obtained them by the oxidation of two main initial products. It was flake graphite powder and graphite foil, like by the industrial name, it's Graflex, as you all know. So using the Hammers method, by the different variation and modification, and the samples prepared from these precursors was found to be identical, as you can see. So in conclusion, let me say that graphene oxide complexes containing titanium, molybdenum, and tungsten compounds are initially transferred into reduced graphene oxide metal oxide composites, while with increasing temperatures, the oxides are converted into oxygen deficient oxides. At 1000 degrees Celsius, reduced graphene oxide composites containing titanium, molybdenum, and tungsten precursors undergo carburization to form carbides like titanium carbide, molybdenum semicarbide, and the phase which consists of tungsten carbide and tungsten semicarbide. Whereas, as I have mentioned, the graphene oxide zirconium compound complex does not undergo carburization and instead results in the formation of reduced graphene oxide, the zirconium dioxide tetragonal composite. Here you can see the references. Two of them is from our group, and some of them are recent newest publications that helped us to conduct this work. Thank you very much.
Thank you, Dr. Barbakadze, for such a great presentation. Are there any questions?
One question, please.
Yes, please.
Due to your result of
Yes.
this work, what are you expecting from the point of view of future application of such materials?
Yes.
Like,
So thank you very much. So as I have mentioned, it was very interesting for us to see the dependence of temperature and different conditions on the formation of final composites. As I have mentioned on the initial starting of my presentation, all of these materials are used in many fields, as I have mentioned, in wastewater treatment, catalysis, other electronic devices, and so on. So we expect to obtain, as I have mentioned, zirconium revealed the very different as a behavior. It was interesting for us, so we will not stop because zirconium dioxide is very strong materials which can be used because it has so let me say it's very hard material, so it can be in other area. But in our case, all these materials can be used in different electronic devices, and we have contact with the Institute of Metallurgy. So they are promising that after the continuous like studies and investigation, we will achieve good result. Thank you.
okay, thank you.
Thank you very much.
Thank you. I'd like just to refresh presentation rules. We have limitation 5 minutes per one presentation. Just briefly, please. And now, is your Stablovich here now in Zoom? I see that Yuri Semerenko here. Can you present, please, the presentation?
Yes, I'm here.
Okay, please share your presentation.
Good day, everyone. My poster presents the first study of the mechanical and acoustic properties of a superalloy in Cornell.
Excuse me. Can you please make a full screen? Yeah. We cannot clearly see in the screen because of due to small dimension of it.
In my computer, it's full screen.
Maybe you can adjust magnification in percentage or press key tab plus alt.
We see wrong window. This is not the one that is open full screen, but the one with the interface. If you could press Alt on the keyboard and tabulation.
Maybe magnify the region you present.
I try. it's okay now. Oh no.
Now it's good.
Could I start now?
You can start.
Oh, okay. My poster presents the first study of the mechanical and acoustic properties of a superalloy in Cornell MA758 at cryogenic temperatures. This nickel-chromium alloy, reinforced with displaced yttrium oxide nanoparticles, is widely used in rocket propulsion system for its heat resistance and creep strength. While its high temperature behavior is well known, reusable space systems also face cryogenic conditions, making low temperature performance equally important. In Cornell, MI758 was developed by Special Metals Corporation, and it's the subject of their intellectual property. Its exact composition is not disclosed in open publications, which motivated us to determine the actual chemical composition experimentally. The figure 1 represents the X-ray fluorescence spectrum of studied material. In this picture, you can see the X-ray fluorescence spectrum of the alloy at room temperature. The measured composition is approximately 63% nickel, 30% chromium, about 5% copper, 2% zinc, and 0.5% yttrium. These displaced yttrium oxide nanoparticles are crucial for stabilizing the microstructure. Figure 2 represents the mechanical characteristics of studied alloy. Panel A shows the stress-strain curves between 4.2 Kelvin and 300 Kelvin. They reveal two stages of plastic flow. First, a parabolic stage up to about 3 to 5% strain, then an extended linear stage. At 4.2 Kelvin, serrated flow appears immediately after the yield point and continues throughout deformation, with progressively large stress jumps. Panel B shows yield strength versus temperature. At 300 Kelvin, the yield strength is 555 megapascals. At 77 Kelvin, it rises to 850 megapascals. At 4.2 Kelvin, it reaches 940 megapascals. Ductility remains high at low temperatures, sustaining 20 to 30% strain. Figure 3 represents dynamic Young modulus and acoustic damping. Panel A shows the dynamic Young modulus, which decreases slightly the temperature from 241 gigapascals at 4.2 Kelvin to 227 gigapascals at 300 Kelvin. Panel B shows the logarithmic decrement of vibrations, which increases linearly the temperature. This behavior reflects the blocking of dislocation process by yttrium oxide nanoparticles, stabilizing the alloy even under cryogenic conditions. Finally, acoustic resonance spectroscopy at 3.3 kHz in the amplitude-independent regime demonstrates stable vibrational behavior. The acoustic strain is on the order of 10 to the power of -7. These measurements confirm that the alloy maintains a consistent resonance property across the cryogenic range. Conclusion. In summary, in Cornell MI758 preserves a stable microstructure, high strength, and good ductility throughout the cryogenic range from 4.2 Kelvin to 310 Kelvin. These results confirm its suitability for reusable space system that must withstand both extreme heat and deep cryogenic environments. Thank you for attention.
Thank you. Are there any questions or comments?
Okay, one question is maybe I didn't hear. What is the operating temperature of such alloy?
The usual operating temperature in the high region, it's about 1000 Celsius. But the reusable space system also face cryogenic conditions. So this motivates us to investigate the cryogenic range.
Okay, it was my next question. Okay, thank you.
Thank you. And now I'd like to give the floor to Igor Stablovy. With the presentation, copper-based high-temperature shape memory alloys produced by selective laser melting, synthesis and structure. Can you present?
Thank you. Can you hear me?
Yeah, we clearly hear.
Thank you. And I have also a short presentation in the frame of poster session. Now I will try to share my screen. Maybe it. Okay, I think you can see. Oh, title of my presentation you can see. I think maybe I will show you in mode another mode. I think, can you see my screen now?
Is it presentation or poster? Just briefly, please.
I have a poster presentation.
Nice.
I present.
Can we see it?
In the form of PowerPoint presentation. It is good?
Yeah, let's start.
Okay. Here I want to present you some of our results based on the
Sorry. Can you full screen, please? Turn on full screen.
Okay, but here the title of my presentation is not visible. But I will. The title of my presentation.
It's okay. All of us see it.
Okay, thank you. I want to say that as we know, classical method for material synthesis reach the limit of their possibilities, and it is needed to find another methods, another roads to obtain novel materials. On that reason, additive manufacturing technologies are currently used to produce both plastic and using the laser technologies, we can produce higher temperature metallic alloys. And selective laser melting, which also known as laser powder bed fusion, is used to produce alloy parts of any shape and size. And this is a large. Okay. In our experiments for synthesis, we use fiber laser with different power. Here on this figure, you can see the scheme of laser treatment of our materials. After synthesis, our samples were investigated by means of electron microscopy and X-ray phase analysis. As we can see at different modes of laser treatment, which differs from each other by energy density of absorbed laser power, we can obtain different results. For low energy treatment, we have obtained some porosity in our samples, which is due to lack of energy for melting powders of individual materials. Here, for synthesis of our alloys based on copper, aluminum, and nickel, we have used pure components, pure powders. And in this figure, in figure 1, it is shown the results of microstructure we obtained. Phase analysis, X-ray phase analysis showed us that our samples are composed mostly by copper or solid solution based on copper, and also we have obtained martensite and austenite phases, which has shape memory effects. At higher power density, we have obtained smooth surface, which is shown on figure 3C. Here you can see also the traces of laser melting processes. On the figure A and B, there are some examples of obtained alloys at lower power of laser melting process. And phase analysis showed us also presence of martensite and austenite phase, as well as copper-based solid solution. And in conclusions, I would like to say that we studied the transitional morphological states of the samples, which can be regarded as informative model structures that allow for detailed formation of the evolution of the materials from mechanical mixture of powders to a functional intermetallic alloys by selective laser melting. Analysis of X-ray diffraction results of the sample obtained under optimized selective laser melting condition reveals significant evolution in our alloys. It was found that we have obtained the austenite phase and copper based solid solution. And these modes of laser melting provided sufficient heat input for the deep doping of the powder mixture components. And I want to thank National Research Foundation of Ukraine for our support. Thank you.
Thank you for the presentation. Are there any comments or questions, please? Yeah.
Okay, my question is, how did you prepare the initial components, initial powder for the SLM?
Thank you. The idea of this work was to use not powdered alloys, but pure powders of pure components, which was sieved and separated by size up to 20 micrometers. And these powders were preheated before synthesis, laser-based synthesis.
And did you use a 3D printer or you use your experimental?
No, we used only experimental laser system for surface treatment.
Okay, thank you.
Thank you. And now I'd like to give the floor to Oleg Tkachuk with the presentation effect of heat treatment on characteristic of titanium alloy manufactured by different technologies. Dr. Tkachuk, are you ready?
Good afternoon.
Can you share the screen, please, as a post?
Okay, okay.
Dr. Tkachuk?
I see.
Yeah. You can start.
Okay. Good afternoon. I want to present a short presentation titled Effect of Heat Treatment on Characteristics of the 6 titanium alloy manufactured by different technologies. You know that titanium alloy, titanium 6 aluminum for vanadium, is used in medicine because because it has a high strength, a good corrosion resistance, and biocompatibility. But the additive technologies can provide can form titanium implants with good characteristics, but we know that also additive technologies have some disadvantages. For example, structural and chemical interhomogeneity and residual stress. And to eliminate these shortcomings, titanium implants need a heat treatment. So, titanium alloy samples were produced using selective laser melting from the powders, and we conducted heat treatment and according to the following regimes at 800 and 850 degree of Celsius for 2 hours with following cooling and holding. Heat treatment was performed in a vacuum. According to the results of metallographic analysis, the raw titanium alloys has an equiaxial structure, and the additively manufactured titanium alloy has a martensitic structure. It is confirmed by the results of XCD analysis, where we fix only peaks of alpha phase. The increase of microstrain in crystal lattice of alpha phase leads to increase of surface micro hardness. Heat treatment leads to transformation of martensitic structure into two-phase lamellar structure, and it confirmed by the results of XRD analysis, where we fix the appearance of beta reflection of the reflection of beta phase. Also, we obtain decrease of microstrain in crystal lattice of alpha phase and a decrease of surface microhardness. So heat treatment at higher temperature is optimal for titanium 6 aluminum for vanadium alloy. That is explained by the redistribution of alloy elements, release of beta phase, reduction of microstrain in alpha phase, and such structural changes allow to expect high mechanical characteristics of alloy. And should be noted that this work was carried out with the financial support of the National Research Foundation of Ukraine. Thank you for your attention.
Thank you. It is well known that titanium alloy with S6 have mainly alpha structure, and you shown that you have part of beta phase in sample number 3 and 4. But did you investigate the texturing of your alloy? Because seeing XRD analysis on picture 3 and 4, they are clearly seen anisotropy of diffraction. Did you investigate it?
We didn't investigate the texture of alloys after heat treatment. We only determined the phase content of alpha and beta phases.
Thank you. Are there any additional questions?
And one more question. What is the difference of heat treatment you proposed in vacuum with traditionally used in 3D metal tech heat treatment in argon atmosphere? What is the difference in properties?
We conducted heat treatment according to two regimes in a vacuum, and we compared the characteristics of alloys after such heat treatment, but we didn't compare with the heat treatment in argon.
Okay, thank you.
Thank you. And now, Victoria Podgorska, are you with us? Can you present your poster, please?
Hello. Can you hear me?
Yeah, we hear.
So I will try to share my poster. Okay, my screen. And then open my poster.
Can you turn it on in full screen mode? Yeah.
Yes.
We see it. You can start.
Okay, thank you. So, good afternoon, colleagues. My name is Victoria Podgorska. I am from the Karpenko Physico-Mechanical Institute in Lviv. Today, I would like to present our work entitled Influence of Nitrogen Pressure on the Structure and Functional Properties of Coatings based on nitride, titanium, aluminum, gadolinium. It's known that titanium alloys are widely used in aerospace, energy, engineering application, and many different branches because of their high straight weight ratio and corrosion resistance. However, the tribological properties and oxidation resistance at evaluated temperature remain insufficient for many demanding applications, so we still protective coatings are still required. In this work, we investigated coatings deposited by cathodic arc evaporation at Kharkiv Institute of Physics and Technology using cathode, titanium 36% aluminum and 1% gadolinium, produced in collaboration with Zaporizhia Polytechnic University. The main goal of this study was to evaluate how nitrogen pressure during deposition affects the structure, mechanical properties, tribological behavior, and oxidation resistance of these coatings. The coatings was deposited at nitrogen pressure from 0.5 to 3 Pascal. The coating thickness was in range 6-8 micrometers. The substrate materials was titanium alloys VT6. The sample were characterized using SAM, ADX, X-ray diffraction, nano-indentation, tribological testing, and so on. The composition analysis showed that increased nitrogen pressure slightly increase the nitrogen content in the coatings. In the same time, the deposition rate reached maximum at 1 and 2 Pascal. According to X-ray diffraction analysis, all coatings consisted mainly of a single phase, cubic nitride, but mixture, titanium and aluminum. The coatings demonstrated pronounced texture. You can see this main peak and nanocrystallite structure. And importantly, that increasing nitrogen pressure did not change the phase composition. We still have the same phase. Mechanical testing was measured on nano indenter. Showed that the nano hardness increase with nitrogen pressure. The coatings deposited at 2 and 3 Pascal exhibited the highest hardness value, approximately 31-33 gigapascal. Another important part of our work was the investigation of long-term oxidation resistance at 600 degrees in air. The coatings deposited at higher nitrogen pressure. You can see this 2 and 3 Pascal showed significantly lower mass gain during oxidation test. Which indicated improved oxidation resistance. Our X-ray analysis, which I don't show here, indicated that protective layer containing oxide of titanium and aluminum formed on the surface. The express test adhesion test using Rockwell diamond indentation, this is first row, showed that the coatings deposited at 5 Pascal demonstrated better adhesion resistance compared to the other coatings. We also provide a typological study at 2 different temperature, at room temperature and 500 Celsius degree. This studies were carried out under reciprocating sliding motion. You can see this scheme against aluminum ceramic ball. Frankly speaking, all these coatings demonstrated high wear resistance during the tribological test, but after our profilometer measuring, we can estimate that coatings obtained at higher pressure, nitrogen pressure, demonstrate reduced wear drag and improved coating stability. So in conclusion, we can say that nitrogen pressure is a key parameter controlling the structure and functional properties of such coatings. And coatings deposited at 2 and 3 Pascal demonstrate the best combination of hardness, wear resistance, and oxidation stability. So such coatings are promising for high temperature protective application in many different branches. Thank you for your attention, and I will be happy to answer your question.
Thank you. Yeah, please.
It's very nice to see you today at the conference. I have only one short questions. What type of coatings is the more wear resistance?
Thank you for your questions. I also very happy to be online on this presentation. And according to your questions, this is the same coatings with the same system, but obtained with different nitrogen pressure. So we have a little bit different structure. Because of less place, I don't show our results with lattice parameter, with microstructure. So we can estimate that different nitrogen pressure influence on formation different structure. Because of this, we have different properties.
Okay, thank you very much.
And I have one more question. What is the role of gadolinium in your coatings?
Thank you for this question. I expected these questions because it's logical. Frankly speaking, we work on this composition for another purpose. We put this gadolinium in order to obtain a stable anatase structure at high temperature for another application in energy. But when we saw a very high hardness of these coatings, we decided to test on tribological behaviors. So in the future, I will show influence of gadolinium in the system, but for high temperature applications, not tribological.
Thank you. And I know that we don't have much time, but one comment from Alexander Vasilyev here, Victoria. It's nice to see you, but it's a pity that so much information is put into such a brief, form. Next time, we really expect you to give a good, full-fledged oral presentation.
I promise that the next time it will be oral presentation, but with another results.
We will keep you to your word.
Okay, thank you.
Thank you for your presentation. And the next presenter is Yuri Sirik. Are you with us? Are you here?
Yes, I'm here.
You can start.
Sure. Can you see my presentation?
Yeah.
Okay. Good day, dear colleagues. Today, I'd like to present our approach to engineer YAG-based material for high power LED and laser diode application. Traditionally, yttrium aluminum garnet is used as a host for luminescent activators such as cerium. However, in high-power systems, not only luminescence, but also light management becomes critically important. In particular, efficient redistribution of pump radiation and suppression of local overheating require materials with controlled optical scattering. Our idea is to create a light scattering matrix directly within a single crystal by introducing controlled microstructural heterogeneity. For this purpose, we study silicon-modified YAG. The crystals was grown by the horizontal direction crystallization. According to X-ray diffraction analysis, the materials remains predominantly YAG, about 97% with a cubic garnet structure, and the lattice parameter is very close to that of stoichiometric YAG. which indicates that silicon has very limited solubility in the lattice. Instead, silicon forms a small amount below the 3% of secondary yttrium silicate phase. At first glance, this might seem like a drawback, but in our case, this is actually the key mechanism. Due to the segregations during crystallization, this silicate phase form elongated channels-like inclusion, a lesion along the ground directions. The typical size is on the order of 1 to 3 micrometers. Because this inclusion have a reflective index different from the YAG matrix and a strongly anisotropic shape, they act effective internal scattering center. As a result, the material exhibits pronounced bite-like scattering built directly into the crystal volume. At the same time, optical measurements show that there is no significant absorption in the spectral region corresponding to the cerium excitation and emission. This is a critical point because it means that the material remains fully compatible with the conventional YAG cerium-based converters. So we achieve scattering without introducing parasitic optical losses. The total transmitter decreases, but in this case, this is not disadvantage. On the contrary, the initial scattering improves redistribution of the pump radiation, reduces local intensity peaks, and leads to more uniform emission. This is particularly important for high-power laser diode pumping, where thermal gradients and non-uniform excitation are critical issues. Another important aspect is mechanical stability. Despite the presence of secondary phase, the material retains properties typical for YAG. The microhardness reaches about 15 gigapascals, which is even slightly higher than in undoped YAG, and the fractional soundness remains at the level about 2.6 megapascals times square root of meter. This confirms that the material can operate under high thermal and mechanical loads. So, to summarize, we show that silicon modified YAG does not simply change its composition, it enables to control formation of microstructure, which in turn defines the optical behavior of the material. In other words, we move from chemical design to microstructural design of optical functionality. And this makes YAG-C as a promising matrix material for next generation composite light converters for high power LED and laser diode system. Thank you for your attention.
Thank you for an interesting speech. Questions?
Thank you for your presentation. And I have one question. Did you investigate the dependence of crystallographic direction of your material on the, for example, optical properties or maybe mechanical properties?
We don't study this in our future investigation. We have to study this point.
Okay, thank you.
Thank you. And now I'd like to give the floor to Dmytro Homenkov.
Greetings, colleagues. Let me share my screen.
You can start.
Yeah, do you see it?
Nice.
Yeah, okay. So my name is Dmitry Homenkov. I'm from Nizhny Novgorod State University. Today I'd like to present my small poster on the thickness profile formation and dopant distribution in silicon and germanium dope hafnium-2 films grown by magnetron sputtering. So the functional properties of hafnia-based films strongly depend on the uniformity of thickness, composition, and microstructure. However, in radiofrequency magnetron sputtering on non-rotated substrates, pronounced radial non-uniformity is commonly observed. First, we study undoped hafnia-2 films at low pressure from 0.15 to 0.4 Pascal. The thickness profile exhibits a pronounced central peak. The film is much thicker in the center than at the edge, as shown by the black curve. This corresponds to the ballistic transport with an axially peaked particle flux. Increasing the target substrate distance broadens the profile due to geometrical spreading and partial scattering, as shown by black and red curves. At higher pressure, around 3 Pascal, gas phase collisions dominate, and the thickness becomes nearly uniform across the substrate, as shown by the green curves. Classical sputtering models treat growth as a local process and cannot explain these radial gradients. Therefore, we propose a coupled growth model combining spatially resolved particle flux with surface-grown kinetics. The model is based on an axially peaked flux that spreads radially upon reaching the substrate, while limited adatom mobility stabilizes the film structure. We deposited silicon and germanium doped films with the conditions that allow to get uniform thickness. For silicon and germanium dopant, both elements act as hafnium-2 network modifiers. Dopant incorporation is governed by sputtering yield. Since yield of silicon and germanium twice higher than hafnia, we observe dopant enrichment in films in comparison with that from the target, about 22% silicon or germanium in the films instead of about 4% silicon or germanium in composed target. So overall, we show that geometry-controlled particle flux governs thickness, structure, and composition, providing a unified framework for optimizing film uniformity. Thank you for your attention.
Thank you. Are there any comments or questions? There is no question. Okay. Are there any remaining poster presenters who would still like to present? I see that's all for today. Yeah? Yeah? Okay. Dear colleagues, distinguished guests, researchers, and participants, as a scientific secretary of the 10th SAMSONOV Conference, Material Science of Refractory Compound, it is my honor to deliver the closing remarks of our conference. Over the past 4 days, MSRC 2026 has brought together researchers and specialists from different scientific fields and countries for productive discussions, exchanges of ideas, and presentation of new scientific results in the area of advanced refractory compounds and materials. The conference program covered a broad range of topics, including fundamentals of refractory compounds, refractory metals and alloys, ceramics and composites, low-dimensional materials and nanostructures, film and coatings. During the conference, we had the pleasure of hearing 7 keynote presentations, around 30 oral presentations, and more than 70 poster presentations. Participants and speakers joined MSRC from different parts of the world, including Germany, Japan, Georgia, the United States, Ukraine, and many other countries. Such international participation once again highlights the importance of scientific collaboration and exchange within the global materials science community. At the moment, the evaluation of student presentation is being finalized. In 3 students categories, the winners will be announced shortly after the conference closing ceremony, followed by the presentation of conference awards. On behalf of the organizing committee, I'd like to sincerely thank all keynote speakers, presenters, participants, session chairs, reviewers, sponsors, and everyone who contributed to the organization and success of MSRC 2026. We highly appreciate your participation, scientific contributions, and active discussions throughout the conference. We hope that the conference has provided not only an opportunity to present research results, but also a platform for new ideas, collaborations, and future scientific developments. Thank you very much for being with us at MSRC 2026. Now, I'd like to give the floor to Dr. Vasilyev.
And one more thing, yes. I would like to call here the people who made this event possible for all of you. That is the organizing committee and a co-chair representing the Kyiv Polytechnic Institute, main venue for our conference this year. So you already saw the Professor Yuri Bogomol, please, as a co-chair. Please come here. We will just wish everyone everything good and call with that. Professor Yuri Bogomol, a co-chair of the conference. Dr. Vitaly Shermet, you already met him today several times. He's scientific secretary of this conference, and it's a debut work of Vitaly. He was really helped by Marina Storozhenko, who has more experience in that and who worked in tandem. Then a lot of work was done to prepare your abstracts, to make them ready for the conference and for the future book of abstract, and that is mainly work of Olena Olifan here, but also on the technical side by Vladislav Billy. Vladislav Billy, we are going back and back. Please stand here. All the materials that we had to prepare for this conference, and there are many of those, especially for the offline participants, as well as coffee breaks and everything related to what we needed to get from outside suppliers and so on and so forth. That was a work of Dr. Alina Makudera. Please come here. And where is Dmitro? And the whole thing is possible in this mixed format, and an excellent site that we have, and technical parts are completely thanks to Ivan Luzhny. Please, Ivan, come here. We also have somewhere Dmitro Reznikov, who did Dmitro Reznik, who did a great job to arrange everything around here, around the venue. But unfortunately, he's not present right at the moment. And that's the team that dedicated several months of their time to make this event possible. We thank you. Really, we want to give our thanks for you for submitting your abstracts, for coming here and presenting, and we welcome you to come to our conference next time on next 11th edition of SAMSONOV International Conference, Material Science of Refractory Compounds. Thank you very much again, and with this I announce the conference concluded.
Давайте фото зробимо. Подивіться всі на.
Куточок затислись.
Там не напише. Чек вправо.
Давайте тоді туди.
Там два рази буде на полу. Ні, там зараз почнеться на лице буде падати.
А так виключно. І це буде conference concluded.
Ти виключиш.
Найкраще буде, коли ми вийдемо от туди. Руш.
Все, дякуємо.
Дякуємо вам. Стій, стріляти буду. Стою, стріляєш.